Welcome everybody to the PCG Workshop 2020. I'm happy to welcome you all wherever you are, what time you're in. Right, yes, we have just a short announcement before we start. The session is being recorded. If you have problems with being recorded, let us know. We will remove you from the recording by sending us a message on Discord, Twitter, all of our channels, email. Right, so it's time for our first session. So our schedule is like this. We have in the next hour we have 3 presentations of 15 minutes each. There's 5 minutes for questions, and then we will have a short break of 15 minutes, which can also be used for discussions, etc. After that block, there will be 2 blocks of 2 sessions, 3 more blocks of 2 sessions, and we'll finish at 7. Right. I need more screens. Right. I think that's it. The first session will be from Adonis Liapis with the first sort of summarizing the first 10 years of PCG Workshop. And yes, all right. Let's hope for 10 more. All right, Lisa, you can start the video. Here is Adonis Liapis.
Yep, and just as a heads up, so anybody who sent me videos, I have them. If you
right.
okay.
Yes, and we'll give the floor to Adonis as well. Lisa, I didn't hear you.
Yeah, I was just saying, so everybody that sent me videos, I have them. If anybody would prefer to try to do, like if you've already sent me a video, but you would prefer to give a presentation live, you can also do that. Just let me know if that's the case. Right.
All right, I think that didn't go well. Let's see. I think I can start the video.
Oh, I was just starting it. I hadn't started it yet. So I'm about to. Okay. Can people hear the sound or no?
Sounded like it could have been a little bit louder. Yeah, that's too quiet.
Okay, it's very loud on my end, so I'm not actually sure how to fix that.
Have you shared computer sound?
Hang on, let me stop the share.
Hello everyone, I'm Antonis Liapis, and this is my paper on the first 10 years of the PCG workshop, focusing on the past and the future trends. This year we're celebrating the 11th PCG workshop, and I'm really glad to be the first person to present here. But it's important to also look back, and in this paper I'm surveying the first 10 years of the PCG workshop and the papers published there. As you can see in the graph below, there's been 95 papers spanning the years from 2010 to 2019. A little bit on the history side, the PCG workshop has always been held at the Foundations of Digital Games Conference, starting at 2010. In the first workshop that was organized by Rafa Bidara, Ian Bogos, Ian Parbury, Ken Stanley, Julian DeGelius, Jim Whitehead, and Michael Young. Here you can see some familiar names that have been highly prominent in the PCG workshop. Now, I looked at the keywords of the papers, and here's a filtered word cloud, but only 80% of the papers have keywords, and the keywords are given in a pretty ad hoc basis. So instead of looking at the keywords, I had to read all the papers and make up my own survey. There's 4 different surveys I'm going to be covering here. I'll try to make it less boring by showing at least fun screenshots from some selected papers. Now, first of all, one of the common ways to categorize PCG is depending on what kind of content is generated. As you can guess, level generation is most prominent, with 49 papers handling some sort of world or level generation. Spanning from cities, to mazes, to maps, to dungeons, to platformers, etc. Architecture is closely related to world generation, but I've listed it separately because there's different aspects and more focus on the real world. 6 papers focus on architecture, spanning from furniture placement to facade design to building layouts, etc. 8 papers focus on some sort of graphics, either particle effects, 3D models, or 2D art. 8 papers also focus on game mechanics, focusing on generating them and figuring out which mechanics work best. Complete games have been the focus of 3 papers, and 2 of them have actual game generators proposed. One is Game-O-Matic and the other one is Data Adventures. 6 papers focus on generating some aspect of a story, although I use this term broadly to include, for example, the generation of satellite sentences, plots for murder mysteries, NPC biographies, etc. Finally, 12 papers generate something, but that falls outside the different categories I've been looking at. So, for example, we have the generation of language, the generation of Lego structures, the generation of CAPTCHAs for human computation, or the generation of graphs. Looking at the types of genres that this type of content is used for, as you can guess, platformers are highly prominent, with level generation for platformers being the main focus, but there's also been work that generates, for example, mechanics in platformer games. 13 papers don't specifically have a genre, but they are trying to simulate the real world. That spans from character locomotion, city placement, city layout, design, room design, etc. 12 papers have some sort of role-playing game in mind, either generating, for example, missions for role-playing games, descriptions for role-playing games, etc. 12 papers also have some sort of roguelike genre targeted, and that includes action-adventure games, and have been the focus of the early work of Joris Dormans. 6 papers have some sort of serious game application, be it for learning games, rehabilitation games, human computation games, etc. 6 papers also feature first-person shooters, be it for level generation, weapon generation, character class generation, etc. Finally, there's other genres that I'm not covering, but I'm explaining in the paper, including board games, strategy games, mazes, stealth games, etc. Now, in terms of the algorithms that are used to generate content, this is probably the most interesting thing to most of you. 15 of the papers, of the 95 papers, focus on grammars, and these are being used for visuals, for Lego structures, for plots, for levels, etc. Constructive methods was a bit difficult for me to identify, so I'm using the term constructive methods here to include L systems, cellular automata, all the things that we consider traditional, let's say, families of constructive methods. 14 papers have these types of methods, although if you include all sorts of scripted methods, a lot more of papers would have been included. Artificial evolution is present in 14 papers, and it's being used to create visuals, to produce suggestions to the user, to optimize for strategy games, etc. Declarative programming is used in 13 papers, also highly prominent, although I'm bundling semantic constraints, constraint programming such as ASP, all in the same category here. Finally, machine learning has been used to generate content in 7 papers, and most of them are more recent, which I will touch upon later. Now, I've also looked at other types of ways to categorize the papers. So 19 of the papers focus on design tools. That means having the generator at the control of the human user, trying to work together to make levels, mechanics, what have you. 7 papers actually make use of design patterns, quantifying them in some way and using them to generate games, levels, etc. 5 papers actually try to perform some sort of player modeling, trying to adapt the content to the player, to a specific player. While 7 papers actually change the game in real time, so the game has not been fully generated in the beginning, but it changes as gameplay progresses. Interestingly, PCG is actually used also as a game mechanic in 5 papers. Here we see some examples where in Anza Island, the player essentially changes the constraints of the generator through mechanics, and the level changes accordingly. While in Tombs of Temeria by Mike Cook, the player controls levers, which basically control how cellular automata work. Finally, 8 papers are what I would qualify as vision papers, either focusing on the politics and science and general problems of PCG and aspects of PCG, or promoting new ideas such as underdeveloped, underexplored types of content, new competitions, etc. 7 papers use expressive range to evaluate the content, and actually the first paper on expressive range was introduced by Gillian Smith in 2010 at this workshop. So since then, it has been quite prominent in the different papers here. And this brings me to evaluation. So even 92% of the papers that I surveyed at the PCG workshop were technical in nature. Only 32 of them featured some sort of quantitative analysis. That means multiple runs of the generator were analyzed in terms of trends, statistics, averages, etc. Now in the paper I performed a number of analyses of the trends based on year-by-year published papers and their topics, but I'm going to skip to the key takeaways for the purpose of the presentation. Now, deep learning is becoming more and more commonplace, even in the PCG workshop, although it is far more prominent in other fields of AI and generation. But it's also brought new life to methods such as evolutionary computation, declarative programming, etc. Level generation still is highly prominent. It's pushed by the industry, it's pushed by competitions that perform level generation, handy libraries, and platformer games in particular have been highly prominent because they're easy to set up, easy to find agents that are fairly well performing. So ease of use is a high factor for which methods, which type of content are prominent. So if you have a pet project or a pet type of content that you think is underrepresented, then it's important to build a community, not only of researchers, but also of fans and libraries for your type of content. The alternative is to wait for industry success. Maybe Google might reinvent game generation, and then we will have a new spring on that front. But taking into account the current trends and not hypothetical future trends, I think that Minecraft is the most likely to become a PCG favorite, not only because of the GDMC competition, which is gaining traction, but also because Minecraft is investing in agents that can play Minecraft levels, also the MineRL competition, etc. So it is attracting attention from people outside our community. The caveat of this survey is obviously that I'm focusing on PCG workshop papers. 95 papers are not few, but they're not that many compared to the many PCG papers besides the workshop. Moreover, it's not surprising to find little evaluation and a focus on vision papers when you think about workshop papers that are more focusing on work in progress, in discussion. And finally, it's important to say, up until now, FDG has been traveling the world, different places. So wherever it travels, different people might submit. So that might affect trends. I would contend that the PCG workshop, even though it is a microcosm, no doubt about it, it does represent the PCG community. Many of its organizers, past and present, are core pillars of game AI research and PCG research more broadly. But our small, relatively, community also has different interests than other communities. So that explains why deep learning is not as prominent here as it is, for example, for visual generation, for music generation, etc. We tend to think of games more on the functional aspect, focusing more on mechanics, on fitness, on how appropriate it is to a player. So that is a reason why we don't see as much work on deep learning. But this might change in the future, as I noted in my trends. And that's pretty much it. Thank you for your time, and I hope you have questions.
All right. Yeah, okay. So there's room for questions. Let's see. Phil has raised his hand. There you go. So you can ask questions by raising your hand, and I will try to give you the mic. Oops.
Oh, actually, I wasn't raising my hand. I was just using the clapping emoticon. But can you hear me?
Also, please keep your hands raised if you have a question, because there are so many people, it's hard to keep track.
Can you hear me, Daniel?
No, Phil?
Hello?
We can hear you, Phil.
All right, so thanks for the talk, Antonis. I didn't really have a question, but now that Daniel has put me on the spot.
He seems to be having problems.
Can you think about, like, how do you see PCG going in the next 10 years? Like, what's the future of the workshop, and where do you see the, I don't know, PCG going towards?
Right. I touched upon this in the paper a lot. It's hard to guess what will happen in 10 years because, well, you can see what happened with the machine learning insurrection that's going on right now. But as I try to say here, level generation is not going away. Constructive methods are not going away. We've seen trends that were like, it's basically like every year you get at least some cellular automata in because they're easy to set up. You can use them for different things, but easy methods will win, at least when it comes to PCG workshop papers. In terms of the future, as I mentioned, machine learning will pick up, even if it's, it's picking up, but not enough. I think it will pick up a lot more in the future, especially when we combine them with our, let's say, hammers, because we see a lot of work that is focusing on it. For example, combining declarative programming with the machine learning or evolutionary computation with machine learning. This will become more and more common. As I also mentioned, the Minecraft competition can be a driving force. I'm not associated with Minecraft, the GDMC at all. I was actually skeptical of it in the beginning, but if you actually think about it, now with Project Mama, supported by Microsoft, competitions by Microsoft, and all that, there's a broader community besides our, well, let's say, smallish to enlarging community that will be helping the PCG people, bringing us agents that can play, easy to set up, maybe computer vision as well that can play into effect, for example, in MineRL, if I remember correctly. So that's where things are going. Interestingly enough, because I know this is your topic, user modeling has been absent from the PCG workshop for the last 6 years. So since 2014, it has tapered off. Game generation has also kind of like, it had some interest, and now it has been absent for the last 4 or 5 years. So I think we will see the trends that we're seeing, and machine learning will be picking up. Fortunately, one thing that I didn't mention, evaluation is picking up. So even as we go into a workshop, which has more work in progress, we see more and more quantitative approaches doing proper technical reporting and all that stuff. So it's quite exciting to see the community growing and becoming more mature. Who's managing this? Daniel?
Go ahead and read it.
Okay, thanks. So there's a question in the chat. Any thoughts on the progress of expressivity of generative approaches through the years? Is there an approach that appears ahead in this? So expressivity analysis was a term introduced by Gillian Smith and Jim Whitehead in 2010. It focuses on essentially a heat map, which shows where there's more distribution, more in a feature set. There's many different reinterpretations of this. Some of it functional, some of it aesthetic. I think the thing that it has is easiest to read is the heat map. So there's a few other things such as bar plots and all the usual stuff. But I think the most succinct is the original one, which is the heat map, and it's quite easy to understand. And you can definitely see where the generator is going towards and tweak the parameters. So I'll stick with the vanilla. That's okay with everybody.
Okay, I think we maybe have time for one more quick question. If see Phil, if you want to go ahead and ask your question, and then we'll go to the next presentation.
Thanks. Yeah, so I'm sort of into the area of machine learning, deep learning, and that kind of stuff, and I'm just wondering how the community feels about how we integrate that into PCG and how we. So one of the problems I've got is that there's thousands of these papers, like literally thousands every single year of thousands of papers, and I have to essentially cherry pick the ones that I think are kind of in the field of PCG. And so the question is, how do other people approach that sort of problem of filtering out what is an enormous body of work in other fields into our field of PCG? How do you guys do it?
I'm not sure I can answer this question. I mean, I think there's many people here that can answer this question better than me. Isaac, for one, and even Daniel. We pick the one that excites us the most. It's the usual way to do science, right? Like you read a bunch of papers, you filter them because you're not wrong. I mean, it's hard to keep track, but one of them stands out, and then you say, oh, I can really plug that into my pipeline and get an easy prototype with level generation or I already have my level generator and it's easy to plug in. I don't really have a good answer for this. This is open to the floor, by the way, if you guys want to unmute and drop in. Before I go, I wanted to say, I have this big database of things. I will clean it up and put it online. I just wanted to point out that I should have done it already, but it will be online in the next, let's say month after the PCG workshop closes. Hopefully we can integrate it with the PCG workshop site so that it keeps growing every year.
All right, cool. Thank you so much. So we're going to go ahead and move on to our next talk, which is going to be James Wooten talking about procedural generation using quantum computing. So I'll go ahead and get that one going.
Hello, I'm James Wooten of IBM's Quantum Computing Group, where we work on quantum computing. This is a new and emerging technology, so you've probably not heard it being applied to procedural generation before. I've been looking into how it might be done, and that's what I'm here to tell you about. So, first I'll need to convey some idea of what quantum computers are and how helpful we can expect them to be. I'll spare you from all the details about how they work. Suffice it to say that they represent a completely different model of computation than both conventional digital computers and analog computers. They don't just speed up normal software through some quantum magic. Instead, they require a completely different approach to software as well as different hardware to run it on. It turns out that quantum computation can perform some tasks far more efficiently than normal computation. This will enable us to solve problems that are currently intractable. After decades of research, we now know many examples of quantum algorithms that will provide this so-called quantum advantage, and they relate to a range of possible applications, including many that could be relevant for procedural generation. These include solving optimization problems, constraint satisfiability problems, doing graph theoretic analysis, and more. And maybe it's important to note that the kind of things we imagine doing with a quantum computer are typically tasks that we just think of as being out of scope now. They're just too hard, and therefore we either find workarounds or just don't do them. However, with quantum computers, we'll be able to tackle them head on. Anyway, the hardware required for quantum computation has also been in development over the last few decades, but building it is a tricky business, and this is because imperfections are inherent, and our favorite methods to work around them require huge overheads in software. To be specific, one important parameter in describing a quantum device is the number of qubits. These are basically bits, but implemented in a quantum way. To run these kinds of algorithms, we need many thousands of qubits, which is not something we are going to have for a good few years. There are also a bunch of other important considerations which mean that we really shouldn't compare devices using qubit number alone, but since we won't be drilling down into those details, let's just continue to use qubit number as our main metric of comparison. Currently, we do not have many thousands of qubits, or even just 1,000. We don't even have 100. The largest device that can be used at the moment has 65 qubits. That is not enough to run the flagship quantum algorithms that we know and love, but they do have the potential to offer results that conventional computers cannot. This is demonstrated by the hardness of emulating these devices. If you wanted to do something like the ones shown in this picture on screen, this has 53 qubits. If you wanted to run an arbitrary program on this, then you'd be looking at doing something like booking the world's largest supercomputer for a couple of days, even to make the attempt. So it's a pretty huge computational task. This means we live in interesting times. We have hardware that can offer unique answers, but our decades of research have not prepared us to ask the right questions. We know that these computational devices are capable of doing things that other computational devices are not, but we just don't know how to crack those things out in a useful way. So, as well as the biggest and best of current devices, there are many at the more modest level of around 20 qubits, and there's a whole bunch with up to 15 qubits that have been made available to the public for free by us at IBM, and you can see the names of some of them on screen at the moment. Also, we've been building some great emulation software to aid in the design and testing of quantum software and quantum hardware. And though it's a massive computational task to emulate more than around 50 qubits, for up to around 20 qubits, even your laptop is really great at it. And this combines to make 20 qubits an important landmark, because whether we use the real quantum hardware that is easy to get at on the cloud, or emulation that is easy to get at on our own laptops, it is really easy to run quantum software targeted at this level. So, what does this all mean for procedural generation? Well, that depends on which of these three eras you're looking at. There's the era of many thousands of qubits, where we will be able to run the kind of algorithms that we've been thinking about over the past few decades, the kind that you'll find in textbooks and with big Wikipedia pages. And with these, we'll be able to get new tools for procedural generation. Most of these will be wrapped up in a function that you just have to call without even thinking of the quantum behind it. And that will go off to the cloud, it will give you your results back, and you'll be able to use them for whatever you need to use them for example, in optimization problems and constraint satisfiability and graph theoretic analysis, as I mentioned earlier. So with these, we'll be able to do unique things for procedural generation using this new technology. However, that's still a few years away, and at the other extreme, quantum software targeted at the 20 qubit sort of level will not be able to do anything unique. The very fact that we can run it on an emulator means that you don't even need quantum hardware. However, can we write some quantum software targeted at this level that can do something useful, something that people will actually want to run, and it will give some real-life end users something that is useful in a real-life situation? Because if we can achieve this with even 20 qubits, it means everything above that also has the potential to be useful. So as the technology improves, as the hardware gets ever more sophisticated, we will be able to explore ever more sophisticated ways of doing useful things with quantum computation. We'll begin by making tools that we probably wouldn't have thought of if we weren't thinking in terms of quantum software, and at some point we'll move on to things that we could not do without using quantum hardware. This is the point known as quantum advantage, which is a big obsession for many people in the quantum computing community. However, for me it's more important to be useful, whether that uses real quantum hardware or not. So let's not get ahead of ourselves. The first step towards this era of exploring this new world of expanding usefulness is to prove that even quantum software for up to 20 qubits can be useful. So let's do that. So, procedural generation means we need to generate something, but what? Terrain generation is a classic, so that's what I started with. And a classic tool for terrain generation is Perlin noise. It would be great to make something that was as useful and became as ubiquitous as Perlin noise, but quantum. Now, I can't say that I've achieved that. What I really went with was a much less sophisticated method for terrain generation, which is where you create a bunch of random points which are concentrated where you want high ground, and then apply a blur effect. Implementing something like this seemed like a more attainable goal for a first step, so that's what I did. And for this, what I need to do is find a way to encode height maps as quantum circuits. Quantum circuits are basically quantum programs expressed in the machine code of quantum computing, which is how we mostly think of quantum software at the current stage. And so we need a way of representing a height map in terms of that machine code, and you can see an example of a very simple height map and a corresponding quantum circuit here in this slide. Now this quantum circuit isn't actually the one that corresponds to that height map, admittedly, but it's the kind of thing that you would see. Okay, once we have the ability to encode height maps as circuits, we can manipulate them in the form of quantum circuits. The encoding I use focuses on squeezing as many points into as few qubits as possible, which doesn't leave a lot of flexibility to offer much high-level control. However, it does mean that pretty much any way of changing the circuit you can think of will induce some kind of interference effect. And mostly I work with well, basically parameterized operations, which if you have the parameter at one value, they do nothing. If you have the parameter at another value, they correspond to a bit flip, flipping the value of the quantum bit from 0 to 1. And everything in between is something in between. So I apply this to all of the qubits in the circuit, and then I can look at how the height map changes as the fraction is increased. So here we have a very simple seed image we start off with, just 2 pixels bright, and then we begin to apply this parameterized operation, and the brightness begins to leak into neighboring points, having something like a blur effect, although it's quite different than a standard blur. As this increases, you start to see interference effects, which is something you definitely don't get with a standard blur, culminating here in them resulting in this interference pattern, which is a checkerboard pattern. Now, this is not a pattern that you always get. It's one that you get from choosing these two specific pixels, which is why I did it. So with other seed images, you'll see different journeys starting off kind of as a blur, but then inducing interference effects, which creates interesting textures. So with this, I made textures and used them to create interesting textures for terrain generation. Basically, I started off with a very simple plan of what my island was going to look like. Then I used a seed image, which I applied the blur to, and I applied the blur quite strongly in this case, so it doesn't look like a blur at all really. But it is a texture which is not just random pixels. There is continuity here. There is the high pixels are typically near to low pixels and vice versa. Oh, sorry, high pixels are typically near to other high brightness pixels. Low brightness pixels are typically near to other low brightness pixels. And then by splatting these textures all over the simple plan of the island, you get a nicely textured island, which I think looks nice both in 2D, as you see here, and also if you render it in 3D in something like Minetest. Images are basically just 3 height maps stuck together, so we can also encode those. One thing that we can do in this context, which I think is quite interesting, is use teleportation-like effects, because teleportation is something that happens in the quantum realm. It's something you can write a quantum program for, and by doing so we can get interesting transition animations. So that's what you see here with these very pixelated I to a B to an M to a Q transitions, although you can also do it on higher res images. Also, we can use it to encode other forms of data, such as music or Mario levels. Here you can see the classic 1-1 that was encoded in the quantum circuit, and then as the level goes on, more and more of these interference effects are implemented to make it look less like what you might remember from your childhood. And yeah, so these are ways that I have used it myself. However, if we really want to argue that it's useful, then we have to see examples of other people, external parties that find it useful in their actual things that they are making. So there's 2 main examples of this. One is in a game that's currently being developed called Clay: The Last Redemption, and you can see here a slide from a presentation from the game studio that's making that. It's also been used by an artist called Libby Healy, who's based in London. So given that it's been used by these parties, it is obviously useful. However, it's important to note that in both cases the quantum origin of these results has been an important selling point. So the algorithmic provenance, that this is coming from the quantum region of algorithm space rather than just being sparkling linear algebra, is important to how it's used. In the game, as a sci-fi game, it's got a sci-fi aesthetic, and using a quantum algorithm as part of the procedural generation can help add to that. Also in the art has been done to explore notions from quantum mechanics. So the results don't completely stand on their own. The quantum origin is important, but it is a start, and it's something we can build on as we find increasing usefulness for quantum computation in procedural generation. So the conclusion is, even now we can make quantum software that's useful for procedural generation, and we're going to build on this even more. You can try out this quantum blur for yourself. It's on GitHub, both in its original Python form and also a Unity plugin. Also, this is not the only procedural generation work I've done with quantum computing. I looked at something else, which I presented at the IEEE conference on games last month. You can check out that paper on the archive. You can learn more about Clay, and you can follow me on Twitter. That is all I have to say. Thank you for listening. Okay, I have to stop pacing around now, I guess. So are there any questions? Well, I saw one question in the chat, and I'll just jump in and answer that if I may. Someone asked if the quantum indeterminacy is important, and in what I've done, and I've tried to make it so that it isn't. So I've tried to not use the randomness of quantum computing at all, because procedural generation is not supposed to just be randomly generating things. Often it's deterministic given a seed, and I wanted to explore more of that rather than just lean on the whole quantum is random, so let's use it to do random stuff angle. So I always then feel a need to explain that, so that's why I wanted to jump in and make that clear. So is there anything else?
Yep, there's a note in the chat. Antonis has a question but can't raise his hand. So you want to go ahead and ask that one?
Sure. Sorry. Really interesting stuff and really novel for most of us here. The question is, I guess, I'm not sure what you're trying to do. I mean, these are kind of like tech demos of the things that quantum computing can do for BCG.
Mm-hmm.
What's interesting to me is the affordances of a new method, right?
Yeah.
Can this kind of method, we've seen terrain generation for a while. The question is, what can it bring that we couldn't do before? And is there some sort of new game, for example, that can come from the randomness from the teleportation, from the quantum aspect of things?
Yeah, so with what's been done so far, I've very much been trying to make it work on the technology we currently have. But a lot of the uniqueness will come with the technology that we will have one day. So there will be speed ups in various types of thing, like optimization problems and constraint satisfiability problems, as I said, which will, I think these are sometimes things that are hard to solve and you just give up. You think, I can't maybe do this optimization. I can't do this particular thing. So you find ways around it, but you'll have a new suite of tools that you won't have to find ways around it. And I have to be kind of hand-wavy there because we have to see how the technology develops, because at the moment we don't know, like up to a factor of 10 how fast this thing will be, which is the difference between making it usable and not usable for certain applications. So we have to explore it as we go and try and come up with new things as the technology proceeds. But I do have these ideas that in 10 years you will have functions you can call that you could not call before. Yeah.
Okay, Isaac has a question.
Yeah, this is kind of related, but I'm sitting here thinking about like different PCG algorithms. You mentioned like constraint solving and so forth. But I'm curious as to what kind of algorithms you see as being most amenable to taking advantage of the quantum computer.
Yeah. So one thing that I find interesting, and perhaps also in the nearer term, is that there's a lot of research going on into ZX calculus as a way of mathematically representing both sort of grammatical stuff and natural language, but also quantum computing. So it seems like there will be some sort of natural language, so they are mostly looking in terms of how to use quantum computing for natural language processing, but I think it would be something good to look into grammar-based methods using that. So that's one thing I'm going to look into soon myself. And I suppose what I'm willing to invest my own time in is a good answer to that question.
Right, cool. Thank you so much. I think in the interest of time, we are going to move on to the next presentation. But again, everyone, feel free to keep the chat going on Discord and elsewhere. This is really fantastic. Okay, so our last talk for this part of the session will be procedural content generation of puzzle games using parameterized generative adversarial networks, and Andreas Hald's going to be doing the presentation, which I have recorded, so I'll get that started. And just, by the way, so the way my computer is set up, I can't see the chat while the screens are going, so message me on Discord or something if there's some sort of like problem with sharing that we don't see.
Hi, my name is Andreas Hall, and I will be representing the research that Jens Stockman and I did together during our thesis, and which we turned into the paper Procedural Content Generation of Puzzle Games using Conditional Generative Adversarial Networks. Our research is focused on the problem of auto-generating game levels by using the deep learning architecture Conditional Generative Adversarial Nets. We find this line of research interesting because game levels designed with GANs are focused on generating discrete data representations, and this stands in contrast to the more classic and state-of-the-art GANs such as StyleGAN, StyleGAN2, and BigGAN, which are more focused on numerical data such as image generation. We also find this line of inquiry interesting because game level design are very game specific, and it thus allows for creative ways of introducing conditions. For example, where Super Mario is a continuous grid that you move horizontally from left to the right on, and Zelda is a grid that an avatar can move in 4 directions on, encountering different enemies, puzzle games, like the ones we're concerned with, is mostly a static level shape, where the combination of tiles changes as we collect different pieces. Finally, our motivation for doing this research was also to turn it into a mixed initiative method tool down the road, where game level designers can kind of utilize GANs to maybe create the first drafts and then finalize game levels. And these game specific requirements and the goal of mixed initiative methods had a great impact on how we decided on the conditions that we wanted to feed into the GAN. So let us try and turn to those now. The first feature that we find is very important to the puzzle game genre is the level shape. Color islands, such as the ones we see are being popped up here, are also very important because they kind of represent for whether the level is possible to begin or continue during a playthrough. Then there are these blockers, which are the non-clickable tiles, such as this flower with an additional bubble blocker on top. These are often part of the collectibles that you are supposed to collect to finish the level, and that says something about how well you do in the level. And then there's the more general piece distribution, such as how many pink, how many green, and how many orange are there, how many blockers are there of different types. All these makes up the total of the level, so to speak. And then there are the local patterns. These aren't as obvious in this level, but they should be more obvious in the one underneath, where these hedges kind of make a downward going line that serves as a kind of theme within the larger level shape. Finally, we also have the sheer amount of unique pieces, and by this I mean, for instance, the pink, the orange is a unique piece each, but when it comes to the blockers, which on the top image we can see, for instance, can be kind of tiled up on top of each other. What I mean is that the amount of unique pieces and the combination of these unique pieces quickly grow to quite a large amount. And some of these we managed to turn into conditions that go for the level shape and the piece distribution. And the local patterns that we discussed are sort of part of our visual evaluation, which we'll return to later. And then we have the many unique pieces. This is an obvious challenge to representation, and for that reason, we want to turn to how we actually managed, how we represented these tiles. In the end, we decided on using a condensed version of the levels that has a level shape layer, a blocker layer, and the color layers from 1 to 6. While this might seem like a heavy reduction from all the possible combination of tiles, we found that this representation still contained some of the desired attributes, such as level shape, color islands, and the aforementioned local patterns that we found prevalent in most maps. And with that, we'll give a brief overview of what GAN architectures that we drew our inspiration from and how we conditioned ours. The classic GAN consists of a generator network that tries to generate realistic looking samples and a discriminator that needs to guess what are real and fake samples. A vanilla GAN works by feeding in a vector grown from some distribution, for example a Gaussian, and then the generator learns to approximate the real data distribution by mapping this C-noise that's randomly drawn onto the real data distribution based on the feedback that it gets from the discriminator. In addition to the vanilla GAN, we use two additional methods to tweak our GANs. Firstly, we condition our GANs, meaning that we give both the generator and the discriminator some labels that are representative of some particular thing in the specific level. In our case, this is the level shape and the piece distribution. Secondly, we used a different loss function called the Wasserstein distance or the Earth mover's distance. This is a very popular metric within GANs, and briefly explained, it's the shortest path or travel plan for mapping a data distribution A onto data distribution B. Turning to our GAN architectures, as mentioned, we use the level shape and distribution vector as conditions. We developed two different models, the first being the vGAN GPP and the second the CVGAN GP, the difference of which I'll get to now. But firstly, the set noise and the conditional vector, which is derived from the distribution, is concatenated together before it is fed into fully connected layers, ultimately reshaped to a 9x15x7 shape. The level shape, here named the map shape, is afterwards concatenated on the bottom of this aforementioned shape, so we arrive at a 9x15x8 shape. That is then led through convolutions before finally being reshaped back into 9x15x8, which is the final output and thus our synthetic levels. Notice the red lines. The difference between our two models, the vGAN GPP and the CVGAN GP, is that in the case of the vGAN GPP, it is only the generator that receives the conditional input. But for the CVGAN GP, the discriminator also receives a conditional input. And this is going to be a point later on. With that, we arrive at our results. But how did we evaluate our GANs, and how do you normally evaluate GANs? The classic approach to evaluating GANs is in image generation, and this is typically with what you call the inception distance or the Facets inception distance as well, which superficially explained measures how well the GANs have approximated the entire data distribution, such as the categories of items within a data set. This approach is not really applicable for our goal. In theory, we could make something similar, where we measure how well our model has approximated the real levels that it has been trained on. But the problem with that is that firstly, it doesn't really measure how well our GANs has approximated the condition vectors in which we were very interested. And secondly, if we want to turn it into a mixed initiative method, where the designer could feed in a self-designed level shape, for example, the question of how well it has approximated the training set levels is kind of besides the point. So instead, we did the following. To evaluate our generators, we used a validation set of 196 levels that we'd store or saved, and generated 250 samples of each, which gives us a total of 49,000 synthetic levels to evaluate for experiments on each generator. We ran 8 different experiments in total on 2 generators respectively. And due to limited time, I will first start with some of the conclusions that we derived from our research, and I will then turn to a few of the experiments that we found particularly interesting. Firstly, a general takeaway from our experiments is that the CVGAN GP architecture seems to be a general improvement over the vGAN GBPE. This suggests that the complexity of the generator and the discriminator kind of needs to go hand in hand. Secondly, level shape condition performs well and generally places the game pieces within the confines of the level shape. The distribution vector performs poorly, And finally, local patterns is a continual challenge for the generators. One possible solution to this could be perhaps draw on the inspiration from the level shape condition and also feed in a local pattern shape condition to our generators. Let us start with the visual representation and local patterns that we should be possible to evaluate, at least partly visually. Comparing the training images to the synthetic levels, which we have out here in the first columns, and then the closest and farthest synthetic levels in Wasserstein distance, it is quite clear that there is a visual difference between them. First of all, every synthetic level has empty tiles present, which is these kind of bluish-green tiles, and they struggle with the local patterns, although there are tendencies to actually get some of these triangles and downward going shapes, and the vertical distinctions as well. Nevertheless, it does seem to be picking up some tendencies. Next, there is the testing of broken pieces. This is an example of a real level shape and 4 randomly drawn level shapes from the synthetic levels that was being trained on this same shape. Notice that I haven't rounded to the nearest integer, and thus you can see some of the tiles where it is still somewhat unsure as to whether or not to place them. I did this because I wanted to show how clearly the generator adapts to the level shape condition. In other words, it's not very far from actually being very convinced that the real level shape is exactly the one we have fed in. This slide also speaks to the point, again, that the CVEGAN GP generally does better than our vegan GP, and the generator/discriminator needs to be balanced. Then we have the distribution vector error to consider. This image shows the result of subtracting the real distribution vector from the synthetic distribution vector that we extract from a level after it has been generated. And ideally this error should be 0. And I think there is nothing else to say here. Then clearly it has not adapted well to this condition. Next, let us consider the expressive range of the generators. In this first expressive range experiment, we measured the combination of number of color islands and number of unique pieces within a level. Again, the CVEGAN seems to be doing better than the vegan GPPE at approximating the real data distribution. However, they both overshoot with regards to the amount of unique pieces and underperform with regards to the number of color islands that are typically to be found in a level. And with that, we once again arrive at our main findings and the future works. So, just to reiterate, the CVEGAN GP generally performs best of the two architectures, and going forward, the lesson of balancing the generator and discriminator will be an important building block in hopefully making progress. With regards to the distribution condition, it is perhaps worth working more on how to impose each distributed number on the specific layer that it's supposed to affect. And here it is perhaps also useful to draw on the recent findings within StyleGAN 2 with regards to how well they parameterize the features within images. And finally, the local patterns are a continual challenge, and perhaps one way to deal with them, as mentioned, could be to consider feeding in a local pattern condition layer, the same way that we did with the level share. And this marks the end of my presentation, and I'll now be open for questions.
Okay, great. Thank you so much. So again, if anybody has questions, feel free to raise your hand on Zoom, or if you can't, type in the chat. Okay, cool. So a question from Isaac.
Yeah, so I'm curious about the how the expressive range and other approaches to evaluating intersected, like I guess the kind of bridging the gap between the, I guess, traditional ways to evaluate PCG, like expressive range and so on, and the traditional ways to evaluate GANs. And can you say a little bit more about that?
Yeah, sure. Well, I think that one of the obvious challenges we had was that that there aren't really any predefined ways to evaluate these scans because it's all concerned with image generation. With regards to the expressive range experiments, it was some of the last experiments we implemented, but I can definitely see that if there are, let's say we have a variety of different features that we want to measure if our GANs somehow improve on, then I can definitely see that going forward, this would probably be one of the main ways we would evaluate the GANs as well. I don't know if that totally explains it. Yeah.
Hi, I have a question as well. Andreas, so you just mentioned again that you're generating levels like images, which is tricky when the levels are puzzle levels, right? So a Sokoban level, for example, can have one very tiny difference with a totally unsuitable Sokoban level. How do you handle this? Did you consider trying using this to generate Sokoban levels? And what do you think of this typical feature of puzzle levels?
Hi, Rafa. Could you just restate them? Your mic is a little crunchy in my headphones for some reason. So yeah.
Okay, basically, would this be extendable to all puzzle levels of all puzzle games, or how do can you handle the fact that very small differences in a level can totally invalidate the puzzle?
With regards to how, like, our specific way, if I understood your question correctly, the specific way that we try to deal with these kind of what I guess is functional content of whether or not a level is playable if tiny differences in the level occurs. We had to set kind of a low bar for the playability of a level. The way we tested it was whether or not there was missing if there were any color islands to begin with, because the way that many puzzle games, at least as far as I know, works is that they can kind of generate the puzzles that are gonna or the pieces that are gonna be popping down afterwards. They can kind of generate it and adapt it to how the game board looks right now. So the way that we had to evaluate it was partly if there were any missing color pieces, or if there were any color items, which is, as far as I remember, more than three or more connected color pieces. And the other way we had to do it was if they somehow started placing pieces outside the parameter of the level shape, which was quite a challenging task to begin with, but which it actually ended up succeeding quite finely with. Yeah, I hope that answers your question.
Yes, thank you.
All right, great. Well, thank you again, Andreas, for your presentation. So We now have a break until 15 after whatever hour it is in your time. So feel free to go get up, take a stretch, maybe get a cup of coffee for those of us who it's still morning. So we'll see you back in about 10 minutes. All right, so hopefully people are coming back from the break. Do we have our next presenters here? So this would be Jonas Freaknecht. Maybe are you here? Oh, there you go. Great, I can see you. Cool. And just to confirm, so are you going to be doing your presentation live? Great. Okay, well, let's maybe just go ahead and get started. I think, okay, cool. You can share your screen. Great, I'll let you go.
Okay, now I think it's better.
Yep, we can hear you and see everything.
Okay, great. So minimize this one. Yeah, my name is Jonas Freiknecht. I'm happy to be here and to talk about our work on procedural generation of interactive stories using language models. Okay, in the last few years, some new language models popped up like GPT or a BERT, and they could be used for text summarization, text translation, and also for text generation. And there are many more use cases. We experimented a lot with procedural story generation in the context with a tool called Twine, which is here for creating interactive nonlinear fiction. And the idea came up to use language models to generate those branched interactive stories. The application of language models for text generation is pretty simple. You just input some text and apply the model to sample some output. Here we have an example of Sandra. We input Sandra went to, and the language model samples her favorite museum to drink some tea with a first love mark. So generating text is simple, but what about linking different passages that build up a story? Nick Walton did a great example with AI Dungeon that can be played on aidungeon.io, where you input some text or take some templates to start a story. AI Dungeon continues the story and at some point asks you to input some text or some command to continue the story and generate the next paragraph and the next and the next. And Nick uses a pre-trained language model that's fine-tuned to text adventures. Our idea is a little bit different. We thought about the old adventures from LucasArts where you have 9 predefined verbs. And we wanted to connect these verbs with a suitable entity and generate actions that the player can click just without typing. The advantage is that our games could be played on a mobile phone or just with a mouse or with a controller, in contrast to AI Dungeon, which requires a keyboard and some creativity to continue the adventures. So the question is how to generate these actions and how to find suitable entities from a paragraph. Finding these entities is simple. We use named entity recognition, which is a method from natural language processing and extracts all entities from a paragraph. NAIR exists for, I don't know, many, many years. So what we get when we applied named entity recognition on the first paragraph are some nouns, and we filter some out, like Sandra, for instance, who's obviously the main character of our game, and we further remove non-physical objects, like, for instance, love. How do we do that? We use a classifier in WordNet synthsets who's able to get a class for a noun, and we only keep those nouns of the classes animal, people-made, artifacts, food, and plant. Why do we filter out love? Language models struggle sometimes with interpreting abstract constructs of actions like fall in love or find love or lose face. So we left them out, but they can be reactivated easily in our prototype. So when we have these entities, how do we generate the actions that the player can click? We evaluated 3 approaches, an analytical or fixed verb approach, which is similar to the LucasArts adventure nouns. We have an extracted entity like Mark, and we use bigrams, or trigrams to find the combination of a verb and an entity with the highest probability. In the first example, talk to Mark would, as an example, be the best fitting action. The second approach is a mask-based approach where we apply BERT, which is a language model that is able to look to the left and the right of a position in a sentence and find a word that matches in this exact position. We created some template sentences like she mask Mark, or she mask to Mark, or she mask from Mark, and let BERT find an appropriate verb to fill this gap. And the verb with the highest probability again is taken for the action. The third approach is a generative approach where we apply GPT-2 on an input phrase like Sandra met Mark and generate using the left to right model to have the next sentences sampled by GPT-2. And the action is just the next sentence. We mostly use the mask-based approach. The analytical approach is very narrow-minded. 9 verbs are definitely not enough to create a believable game. And the generative approach does frequently return actions that are no actions or no commands. They are just sentences and do not really feel like the player can take part in the game. So the mask-based approach worked well. And we have some special work that we work with, like pick up or a synonym like take, buy, or get. Whenever such a verb is picked for an action, the item or the entity that comes in combination with this verb is added to an inventory that remains in a long-term memory of the player. These entities in the inventory can be used. Our game mechanic produces randomly use actions that can be applied for items. So when a ball, for instance, is picked up, the game might create an action use ball, and the ball can be used in the game. We furthermore have a combine action when a player has 2 or more items in her or his inventory. The items can be combined. We offer a combine action. Generating the combination can be quite funny. We have a template like she combined iron and hammer to receive a mask. So we use BERT again to let the language model fill this mask position. And the combination of iron and hammer can be a blade, a handle, a shield. These words are actually found by BERT. When item 1 and item 2 does not really fit together, the combinations could be quite entertaining. So we have a paragraph, some linking actions that the player can click. And what we do next is to apply some templates to convert these linking actions to a believable phrase, like talk to Mark is converted to Sandra decided to talk to Mark, or drink tea is converted to Sandra drank the tea carefully. This is just templating and not too interesting, but it is required for GPT-2 or for the language model in general to work well. We then concatenate the first passage and the action phrase and apply GPT-2 to it, and the language model generates the next paragraph. When we have this new paragraph, we do a combination of the previous texts again, repeat the action generation, apply the templates to get new action phrases, and receive and apply GPT-2 to receive the next passage until the desired number of passages is reached at the end. So this is the entire process. What are the pitfalls in unsupervised text adventure generation? Well, there's a gender bias as in most language models, which is annoying from time to time. When, for instance, we want Bird to find a word for he, verb here, the ball. For a male character would catch the ball and a female character would drop the ball. There's research to identify and reduce the gender bias in language models. We think it should be done on language model level because it's very, very hard to filter that out during the story generation. You furthermore have no control over the content, which is very, very often inappropriate. For children, for instance, there's research going on to detect inappropriate content, and there should definitely be some kind of control mechanism if this game should be online, playable online, for instance. We furthermore have a performance challenge. Depending on the number of actions the player should be able to click, the generation time for an entire story can get pretty long. For a story with 6 paragraphs and 7 actions, there are 350 paragraphs to be generated. On an average GPU, the generation time for 1 paragraph is about 20 seconds. Challenge for the future should be to reduce this time. We furthermore did not only generate a story, we also wanted to know how good are our stories. So we try to measure and improve the coherence. We did a measurement via latent Dirichlet allocation on the basis of 10 topics. And the first thing we tried is to do a character alignment. With each new paragraph, a language model normally introduces 1 new character, which is quite a lot. Even books like Lord of the Rings or Harry Potter don't have so many main characters. So we set a limit of 8 and try to replace new character names with character names already known, which brought a minor influence on the coherence. What really helped is to add reminders. When the player has items in her inventory or has already visited some places or met some characters, we added phrases in the new paragraphs to remind the player of these items, places, and characters. And we do this by just simply adding a new sentence to a new paragraph. And by this, the language model is aware of this item again and includes it in the generation of the new paragraph. We furthermore experimented with influencing the sentiment. We were able to remove so many changes in sentiment and hoping to increase the coherence, but the sentiment had no influence on the coherence at all. So we created an actual prototype. I will show the link later, which can create a story that can be compiled using TWE2. I just want to show the parameters. We can select a setting like fantasy, sci-fi, select a player name, choose some party members, and choose the action generation method that we've seen before. coming to the conclusion and the next steps, language models can be used for interactive story generation, but the most profound challenge are the generation durations. These are pretty long, and we should try to fix them somehow, either by using cloud GPUs or generating more text in just one generation step. We are still doing research. Game mechanics enhance the immersion. So when you can use items, take items, talk to characters you already have in your party, that lets the player feel more like a game. That's what our evaluation shows. But nevertheless, coherence could be improved, to express it nicely. We hope that we get access to GPT-3 soon and run our tool on GPT-3. We will see. Furthermore, we'd like to include GANs to generate images, to support the story visually, and allow an even better immersion. If you like, you can download the code, improve it, share it, fork it, whatever. It's all on GitHub. Thank you.
All right, great. Thank you so much. So again, anybody who has a question, feel free to raise your hand in Zoom. I guess in the meantime, I'm curious about just since you brought up the issue of the gender bias in a lot of the learned text, I was just wondering if you knew like what methods people would actually be using to solve that. This is outside of my research area.
Yep. I did not go into detail a lot when reading research papers, but one thing I found out is that some people try to normalize the gender. So they remove he or she from the context and replace it by some neutral, I don't know how to find the correct word, by some neutral word, and thus they do it before the training and train the model again, which might be difficult for something like GPT-2, which costs some $1 million. I heard a number of some $1 million to train such a model. So the problem should be more aware at big companies like OpenAI, so that they deal with this issue at the very beginning of training the model, and not only when the model is done, and let all the people who apply the model deal with this issue.
Okay, cool, thanks. So let's do the people who had their hand raised, those questions first, and then the other co-organizers had some questions. So Tim, you want to ask your question?
Sure. I don't know if you guys can you hear me all right? Okay. So it looked like one of the big problems was remembering items in the narrative. What about items that need to be forgotten? So if you use iron to make a blade, you need to forget the iron. You're looking at handling that, or is that not an issue?
It was not actually. When you want to forget an item, you just might shorten the text that you input into the language model so that it does not contain a sword or whatever object. That would be an option. But we never have this issue because remembering items per default happens on a very rare occasion. So you do not have to force a model to forget an item, but you have to force a model to remember an item. That was more the challenge.
Very cool, thanks.
All right, next question, Reamer.
Hello. Yes, I had a question regarding, thank you for this nice presentation, by the way. I had a question regarding the directing what it generates. Do you see opportunities of integrating pattern-based approaches? So like you have something like a hero's journey or something, and this sort of has a structure along which things can be generated. Would that be possible to integrate that with your work?
Yeah, that's a very good point. The only thing we try to bring a story to an end. In the current state, the game runs and runs and runs, and at the end it just ends. So we experimented with introducing some fixed text blocks, like the main character felt the story was coming to an end, and then generate the next parts. This could be introduced to some kind of, how did you call it? Some kind of framework for an entire story, to have these kinds of steps within a drama, like tension is building up, then there is a big crisis and tension is falling again. Would be cool to experiment with. Yeah, but we didn't do this, just for the ending part.
Right. Cool. And then I think for our last question, Isaac, did you want to ask your question?
Well, my original question was like partially covered by what other people asked, but I guess since it's GPT-2, I'm curious if what your approach to retraining it, if anything, was.
Yep. In our paper, we wrote that we explicitly not want to retrain the model, not because it had some bad effects, but to test how good we are, even if we don't retrain it. It would definitely be one of the next steps to do a retraining, especially in terms of keeping it in a specific domain, like taking all books from a specific author, like, I don't know, Dan Brown, for instance, to generate stories in the universe of Robert Langdon, to do a fine-tuning for a very specific domain. That would be interesting. We didn't do it to see how far we get without retraining.
All right, great. Thank you so much. So with that, let's move on to our next talk, which is about Minuet, procedural music accompaniment for textual narratives. And I'll go ahead and stream the video.
Hi everyone, my name is Mehek and I will be presenting Minuet, a prototype for procedural music accompaniment for textual narratives. Now when it comes to procedural music accompaniment, a lot of work has been done on accompaniment to musicians, games, and visual narratives. But less attention has been paid to textual narratives, and here we present mood into note using extracted text, or Minuet for short, which is our prototype for procedural music accompaniment for textual narratives. Now the system takes as input a story, and for each sentence it carries out sentiment analysis to extract the mood from the text, and then it uses that mood to generate music to match the story. Now I'll briefly go over the related work. Now music generation, there can be two big broad categories. One is transformational music, where you take in as input a melody and transform it to match the input melody so that there's a better accompaniment to that given input music. The other are generative methods, which are more recently developed, where you generate music from scratch in a bottom-up fashion. Now, research has also shown a lot of symmetry in emotion and music, and especially this work by Madog in 2018 was really fascinating, where they developed something called Sentimozart that generated music based on the mood. Now, what it did was that it would take as input human facial expressions and try to identify mood and then generate music based on those moods. In another study by Adam in 2014, they developed something called Odd.js, which is a JavaScript API that they developed for game developers to generate emotion-specific music in their games. And it follows the Thay's model of mood. Now, our work builds upon that of Romanto and Maldivi, which uses Markov chains as well as the Russell circumplex model of mood. And we provide more details about these in the paper. And finally, sentiment analysis is the natural language processing task of identifying emotion in the given text. And most of the work has been done on binary classification, where you either have a positive or a negative emotion associated with the text. And a lot of methods such as support vector machines, recurrent neural networks, and convolution neural networks have been used for these tasks. And more recently, a lot of work has been aimed towards multi-class classification, such as this work by Mohammed in 2017, where they used multi-class regression to assign labels to tweets of mood. And now I will go over our approach. Now, as I mentioned, that it takes in a story, and for each sentence, it performs sentiment analysis to extract the mood and then generate music based on that extracted mood. Now I'll briefly go over our sentiment analysis, which is a supervised learning task of multi-class classification, where the classes are happy, surprise, fear, anger, and sadness. Now we use 2 tweets data sets, and after pre-processing, we had 3,742 tweets. In terms of pre-processing, we had a 12-step process for removing tags, hyperlinks, etc. And we used 5 predictive models. We performed both holdout and cross-validation testing, and we selected the model based on prediction accuracy. Now we'll briefly discuss how we generate music using the extracted mood. We built upon the Romanto and Maldivi model that is based on using Markov chains. In that approach, there are 4 chains per mood for chord, note duration, note transition, octave, and note duration. Now, amongst the 5 moods that we want to predict or understand, there are distinct set of chains for surprise, sadness, and happiness. But they combined anger and fear into one category that they called high negative affect. Now, we gave in a lot of literature and reasoning as to why we selected fear to be represented by high negative affect, and we experimented to develop new set of chains for the mood of anger. What we did was we used the high negative affect as the baseline and modified the tempo, chains in the chord, note duration, and octave to better suit the mood of anger, and we have detailed the approach as well as the results in the paper. Now we'll go over a small demo, and please note that right at the beginning some sound plays just to show the start of that system. This is the system, and after this, right now I'll play. That was a demo. Now this takes us to the discussion and future work. Now, while going through this process of developing the system, we had a few assumptions. For example, we assumed that emotions are conveyed through music, and a lot of literature actually supports that assumption. Another assumption was that emotions are conveyed universally across listeners, which may not always be the case. And this is a good opportunity for other researchers to expand on this work. And based on our internal testing, we realized that we can enhance our prototype by improving the sentiment analysis. And one way to do that is by introducing a neutral class, because more often than not, there can be sentences that do not have a particular mood associated or a strong mood associated with them. And we want to include more data and perhaps better data sets. We currently use tweets data sets, and we think that because it was relatively easily available, but including data sets that actually have textual narratives will definitely improve the model. And finally, we want to experiment with more better predictive models, such as that of the attention models. A lot of research has shown that attention models are better at the task of natural language processing. Now, apart from that, a lot of modifications can also be made to the mood-based music generator. For example, if you notice that in the demo, there was an abrupt change from the sentence that had a sad emotion to the happy emotion and vice versa. And we think that we can make the transitions smoother, and we have explored, or we have mentioned, 2 ways we can do that in the paper. And another way we can improve the music generation is by splitting the sentences into chunks of distinct emotion. For example, if a sentence has both happy and sad emotion separated by the connective but, we can identify that and play separate music, again with smoother transition between the 2 chunks. And then finally, we think that there can be quite a few applications of this work, and to encourage others to incorporate this, we want to make this system as a web-based application where we open source this prototype for others to use and build upon. And one way to build upon this can be to combine this with the generative text or story tools such as Tracery, and that way we can have a system that generates not only the stories but also music accompanying those stories. And we can also include them in a text-based interactive drama. And finally, we can maybe also include it in movies and games by inputting or generating music based on the scripts for them. And that's it. Thank you so much for watching.
Great, thank you so much. So yeah, questions. Okay, and I see there is some good discussion going on in the chat. I don't know if anybody wants to bring up any of their questions they've raised in the chat.
Sure, I have a question. So I was part of the discussion in the chat. We were thinking about how to make this smoother transition between sections, instead of going from sentence to sentence, either generating these chunks with pivot points. And I was thinking about some sort of like emotional feature vector, and I was just wondering what your input is on those different ideas.
Hi there, this is Arnav. I'm one of the co-authors, Max advisor. So there are sort of several interrelated pieces there that factor in terms of in terms of identifying the sentiment. Right now, the classifier sort of gives labels rather than some sort of a range, right? So so that's one issue, and if, we've been thinking about using either sort of some kind of arousal valence like or arousal valence dominance like model to say, well, what if we make this space, and that might make it interesting to explore. And so so yeah, I think we might have to do away with the specific labels, right? The happy, sad. Downstream, that creates an interesting issue because the music generator itself is using these sort of somewhat handcrafted, transition probabilities for the various emotions, and so that becomes a little bit more complex to model. And so, but yeah, if we improve those two, and then we definitely would be worth exploring that in the future.
Great. Any other questions?
Antonis?
Yes. Hi, Arnav. I would actually contend that I liked the fact that they were, abrupt changes, because when you're doing music emotion mapping, it's really easy to make it sound like elevator music, right? So when you got the strong, impactful statement that you got, it was good. Like it was emotional, right? I would say maybe you could do the transitions on the sentence level, what we were discussing on the chat, which is where apparently all the research is, that you could actually just instead break the sentence on the textual level, then show the sentence to the machine, so that you do that, and then you still retain some sort of musical richness. Because otherwise, I feel like if you just transition too much, it will need to be a long story, and the long story will be boring because it's going to be transitioning a lot. You see what I mean?
Right. Yeah, it's kind of an interesting thing that there are even within our group here, there are sort of preferences on how what people prefer when they are reading this, right? So I think there's a general sort of larger, deeper research question on how to represent those preferences, right? Like whether you prefer those sharp transitions, whether you care only about the intense pivot points, as Max pointed out, right? So and how much sort of coherence do you want over what period, right? So and then these are all sort of very particular musical preferences.
All right, cool, thanks. So just as a note on our schedule, if anybody else does have any last questions, feel free to ask them. But looking at the schedule and realizing we accidentally added in an extra 10 minutes for this part of the session that shouldn't have been there. So probably in the interest of not having a 25-minute break in the middle of our days, we can perhaps move things up a little bit, assuming everyone would be here. Ahmed, Khalifa, are you here? Would you be ready to do your... Okay, cool. So you're here. That's great. So why don't we go ahead and take our 15-minute break, and then we'll reconvene at 10 after, whatever your next hour is, and start from there. All right, cool. Enjoy your stretch break. Keep the discussion going if you want. All right, cool. It looks like at least some of us are back. I personally had some cheese. Pretty excited. It was good. But yeah, I suppose we will get started. So Ahmed, I'll go ahead and just play your video.
Yeah, sure.
Okay. The title. Okay, so our next talk here is a multi-objective level generator generation with Marahel. by Ahmed Khalifa and Julian Tegelius. All right.
Paper, multi-objective level generator generation with Marah. So what we're trying to do in this paper is to automatically design a constructive level generator by searching the constructive level generator space defined by Marah language. So what does this even mean? Instead of trying to find levels for our game and build a level generator to generate levels for our game, we will try to search the space using AI to search the space for a level generator that we can use directly in our games that can produce multiple of these levels with the features we want. And that level generator will be defined using a language called Marahil. For people who doesn't know, constructive level generators are generators that's being used widely in the game industry. They are like a group of rules that's being applied after each other to generate the level in the end. And people design these rules really carefully and put a lot of human knowledge and knowledge about the game in order to get really good results. It's being used widely. For example, Splunky uses it, The Binding of Isaac, Slay the Spire, No Man's Sky. And for the other things people might not know is Marahil language. For people who doesn't know that, it's a language introduced by me and Julian Tegelius at Exact 2017, and it's like a context-free grammar language that can describe different types of generator, and we were going to talk about it in details in a little. Some people might ask why I'm trying to do that. One of the obvious reasons is to design a constructive level generator by hand is kind of a little bit of tedious work, and you need to understand really well the rules and everything that's happening in the game. And even if you understand all this stuff, sometimes you want some features that can't be happened easily by coding some rules. It might be happen in simulations, so you can't use constructive level generator. And using search-based generator might be out of the question because search-based sometimes take longer time, especially if using game simulations, and because of that you can't use it online, you have to use it offline. So a trade-off of all of that, we could use all the training time with the simulation and everything offline to find a constructive level generator that incorporate all these features and then use it directly in our game. That will give us like the best of both worlds. Also, one of the things is Marahil is very human readable language. And because of that, if we try to use an AI to find a constructive level generator that can achieve certain features, and then we read that generator, we could understand deeper meaning about our games. We could understand how the rules happens, how this interaction happens, because the rules that's been evolved will incorporate this meaning in it. So that might be a good and interesting avenue to see. And also looking back at every single stuff that have been happening in level generation mostly focus on generating levels themselves, but generating a level generator is not like a lot of people work on it, and I know it's like a more harder problem because it's like a meta problem, so not a lot of people working on it. So it's like was a new and exciting field I want just to engage in and try it. So the Marahil script. That's what you see in front of you. So Marahil, any script in it constitute a constructive level generation, a constructive level generator, and the whole language can be explained using context-free grammar. And what's in front of you is an example of one of the scripts that can be written. Any script consists of 5 different regions. The first one is the metadata, which tell you has the size of the map itself. The next one is entities. It tell you what is the objects that can be in the map. For example, here we can have empty or solid objects. Then there is neighborhoods. Neighborhoods are this local relation between the tiles and themselves, similar to the convolution filters in deep neural networks. And then there is regions, where it defines different areas that can be, we apply the rules to each of them instead of the whole map. And lastly, explorers, which is the actual rules of the generator itself. For example, this is like this generator has 3 explorers where each one do different tasks. For example, the first one, what it do is it fills the whole map with solid. The second one, it empty the center of each region by placing empty tiles in the center of these regions. And then the last one, it connects every single entity with some empty tiles. So we have now one fully connected map with consists of rooms and doorways. So since it's a context-free grammar, the language itself, one of the ways we could like evolve it and find like script is using grammatical evolution. And for people who doesn't know what's a grammatical evolution is, it's like a type of evolution where instead of where the genome is just a group of numbers, and these numbers tell you how to expand the grammar itself. So when you follow all the expansion, you get the script. But in our problem, to make it easier, we decided instead of like expanding the full script, we're gonna only expand from 2 to 5 explorers only. And the reason for that is just like to make it an easier problem and simpler, and might find the solution faster. We applied that like search for generator onto 3 different games. The first one is called Binary. Binary is like this 2D maze of empty tiles that's fully connected. So in order to have a good generator, we need to have all the empty tiles to be visited from any other tile, so all of them are in single region. Second thing, we want that to have a long path in the maze so we can move a lot in it. That's for binary. The second one is called Zelda, and Zelda is this simple game where you have that players that try to grab a key and go to the door and try to avoid monster in the way. So to have a good level generator, we need to make sure we have 1 player, 1 key, and 1 door, and not a lot of enemies, so it's not too difficult to play. And the last game is called Sokopan, where you are this warehouse worker that try to push crates on certain targets. And of course, to have a good level generator, we need to have at least like 1 player and then some crates and an equal number of targets. And it needs to be solvable, like you can find the solution for it using a BFS algorithm. So in order to evolve that and find the generator of our like explorers themselves, we decided to do some preliminary tests using just objective-based evolution. And we find that when you try it on the binary problem, we found that we can't find any decent generators, because when you have everything fully connected, you have very short path lengths, and we have a very long path lengths, so you have isolated areas. So we were like, oh, there is a trade-off. So we decided instead of using just normal objective-based to use multi-objective, and we use NSJ2 for that. We evolved a population of 500 chromosomes for 2000 generations. And instead of starting from an empty map, we decided just to initialize this with random noise. So the explorer doesn't spend time just to maybe to populate with some random noise that need to filter later. And because it's a level generator, in order to calculate the fitness, so we sample 50 generated levels from it, and then calculate the fitness for each one, and then take the average over them. For the binary problem, as you can see in front of you, this is the Pareto front. The Pareto front of the binary problem contain like some like chromosome, not all of them, because they dominate other chromosome. And as you can see, there is no like chromosomes that can like solve both dimensions. So in order to solve a dimension, you need to get score 1 on it, and if you score 0, it means you're very far away. But we can't find any chromosomes that can do that in our current problem. So when we found this like inversely proportional and the trade-off, so we decided just to pick one of them and look like deeply in it, and we picked this one because it had like a decent path length improvement and not very small amount of number of regions. So on the left, you can see the code for the generator, and on the right is just a random initialized map, which you're going to be modifying with each step of that generator so we can understand. So that generator consists of 3 explorers. The first explorer, what it do is it tries to connect every single isolated area using big chunks of empty spaces. And doing that, you have a fully connected map, but at the same time, you have a very open space because you're using big chunks of it. Then the second one do nothing because it's actually also another connecting that connect isolated areas. But since the first one connected everything, the second one usually doesn't do anything. And then the third one, what it do is it try to place solid tiles in the middle of the map. when there is empty spaces. And by doing that, it made sure that the map is kind of like a ring or like maybe a loop. And because of that, you have a long pass, because this is kind of long because you need to go in the loop. But at the same point, because it's being placed there one by one, sometimes you put tiles that cause isolation and the small amount of region, which could be easily fixed by like adding maybe another like explorer after it that connects this isolated area, and that's it. For Zelda have 5 different fitness functions, and because we can't like show the Pareto front of 5 dimensions in a 2D plane, we decided just to split it onto 3 graphs where one of the fitness functions is redundant. And unfortunately, all the 500 chromosomes are in the Pareto front, which means they don't dominate anything else. All of them are in the Pareto front, which like make it not like find any good solution. And even the best one we could find, which can generate up to 14% kind of playable levels, is that generator. So that generator consists of 2 explorers. The first one does nothing, while the second one, it just adds some solid tiles based on a noise function. And by doing that, it erases some of the extra tiles that's there. It's kind of like acting like a filter to remove some extra tiles. And because you're removing some extra tiles, there is a high possibility you will end up having maybe a playable level at some point. So in Sokopan, it have also 4 different fitness functions. And because of that, it has the same problems as in Zelda, because it has a lot of dimensions. And all the 500 chromosomes are in the Pareto front, and even the best one have only 5% of playable level generated. And it does the same behavior, but now the 2 explorers, the first one acts as a filter, where it replaces extra players using a noise function into targets, and the second one does nothing. But as you can see, like when you act as a filter, there is a chance you might have some playable level. For example, if you look at the lower left one, that could be playable. It's not playable, but let's say the noise have something similar, but the boxes were not stuck in the wall, and then it replaced a player with a tile, a target tile, and then it fixed it. It could be played, and that's why it gets like 5%. So overall, we could now generate like level generators. We can find generators using AI, and these generators are really interesting because we can read them and go through them and understand what's happening line by line. Although it might not be 100% like sometimes readable because it's used noise function, do filtering, and stuff might be just not human understandable. It's a lot understandable compared to other techniques that might not easy as to understand, such as neural networks. But on the other hand, we have a very poor performance in this generator. The binary couldn't solve any problems, but they have like an interesting like generator where it just creates these loops. And on the other hand, Zelda and Sokopan was just acting like noise filter, which was not very interesting in my point of view. So for future work, I would like to investigate what will happen if we start from empty. Does it end up just adding noise and then filtering it for Sokopan and Zelda, or it will start learning better rules about how to add elements to the level? Another one is, what about if we give less restrictions? So instead of 2 to 5 explore, what about like giving 10 or more, or even the whole script where you can have regions and all that stuff? Another thing is, as you see in Sokopan and Zelda, we have too many dimensions, which cause the multi-object evolution to put everything probably in the Pareto front. So maybe we need to use a different algorithm, or try to reduce our fitness function, or use a quality diversity algorithm that doesn't care about the number of the different dimensions we are using. Another thing which we notice is using the Adversarial operator was not the ideal, because, for example, if you have two different generators, one of them generate mediocre content all the time, and the other one have 50% chance to generate amazing content and 50% chance to generate garbage content. Both of them, if we take the average, they might be really equal, but they are totally different. One of them have a big standard deviation and weird output, you don't expect what's going to happen. Another one is more consistent. So maybe we need to find a better way to represent, to incorporate the standard deviation or something, so we have these generators that are more consistent in generating good content in the end. And thank you. That will be the end of the presentation. And if anyone now have any questions, feel free to ask it.
And just as a reminder to people, you can ask you can raise your hand with the raise hand feature, or you can type in the chat. I see at least one raised hand. Oh, sorry.
Okay.
Try to automatically unmute you.
Yeah. Hi. Yeah, I have a question. You chose a language-based approach, which, by the way, I love. I really like this. So what do you think the benefits are for choosing a language as a way to control your generator?
Yeah, like one of the most obvious one is just like it's readable. Like if you have a script in the end, you can read it and just see what's happening, and even debug it or like modify some stuff. Like, oh, that look interesting. If I change this parameter or like add this thing, that will be a lot better. So it will help also like collaborative with humans, because you could just like go in and modify something in it. And that was the main reason behind it, because I have another paper, but for aid, which I use instead neural network instead of a language base. And like you can't easily just go and modify the weights. You need to have like use an active learning or something after you train the network to modify some of these weights. But you can directly say, oh, that weight I don't like this weight, let's just change it.
Yeah. So adjusting, modifying it, reusing it, maintaining it, sharing
understanding
it. There's a lot of reasons for it. Okay.
Yeah.
I found your first paper from 2017 in a mapping study I did on languages for games. So it's nice to see that actually the language helps to progress the research and add new stuff to it.
It took longer than I expected, but yeah, that was planned from the first time we did the first paper.
Sorry, that wasn't really a question. Thanks for the presentation.
You're welcome.
If there are any other questions, I think we have time for one more, since we did speed things up a little bit. Otherwise, we can queue up the next presentation.
All right, yeah, so our next presentation will be on sequential segment-based level generation and blending using variational autoencoders.
Hi, I'm Anurag Sarkar from Northeastern University, and in this presentation I'll be talking about work that my co-authors at Cooper and I did, where we introduce a new PCGML approach that combines the use of a modified variational autoencoder and a random forest classifier to be able to generate whole platformer levels that can progress in multiple directions, while still using late variable models with fixed size inputs and outputs for training and generation. So what was the motivation for this paper? Well, in recent years, we've seen several works using latent variable models such as GANs and VAEs for generating levels for platformers and dungeon crawlers, as well as blending of levels in some of our own previous work. And what these models do is that they learn a continuous latent representation of the input levels, and so enable not just level generation via sampling, but also operations such as latent vector evolution to generate levels with certain characteristics, as well as interpolation to allow applications such as blending of levels from different games. However, the drawback of these models is that they tend to work with fixed size inputs and outputs, which in itself wouldn't be a problem, but is compounded by the fact that when working with machine learning for PCG and games, we don't have thousands of whole levels to train on, and so these models are trained using small segments of levels, and in turn learn to generate level segments rather than whole levels. And so as a result, existing methods generate whole levels by manually combining together generated level segments. Now this can work reasonably well for dungeon crawlers where gameplay can take place in discretely generated rooms and then the rooms can be connected to form the whole dungeon, as in the work of Gutierrez and Schramm. However, for unidirectional platformers like Mario, it can work well enough, but isn't ideal since randomly sampling successive level segments does not ensure that the newly generated segment logically follows from previous ones, even if combining them one after another yields something that is playable. And where this approach fails completely is generating playable, coherent levels for games that can progress in multiple directions, both horizontally and vertically. So here we have a level for Mega Man that progresses both to the right and upwards, and using existing methods, we can't reliably generate these types of levels by combining successively generated segments, because for example, if we have a level that is progressing upwards, it's very possible that the next randomly sampled segment will progress to the right, so we'd have to keep sampling repeatedly until we find a suitable next segment for the level. And for similar reasons, prior attempts at blending levels from games that progress differently had to be done either in segments or by generating blended levels by taking turns and using level generators trained separately on different games. And so the problem we wanted to solve with this work and what we want to be able to do is to generate and blend whole platformer levels progressing in multiple directions while still using latent variable models like VAEs and their fixed size inputs and outputs. And so the solution we came up with was a two-step approach where in step one we modify the VAE so that rather than training it to reconstruct the current input segment, as is the norm, we train it to reconstruct the segment that follows the current segment in the input game level. That is, decoding a segment's encoding yields not the segment itself, but the segment immediately after it in the level's progression. And then in step two, we use a trained random forest classifier to determine whether the next segment should be placed above, below, to the left, or to the right of the current segment. This modified VAE classifier combination thus gives us a hybrid PCGML model that, starting from an initial segment, enables us to generate coherent platformer levels of arbitrary length, progressing in multiple directions, while still working with fixed-size segments. Additionally, it also enables the generation of not just segments that blend together multiple games, but entire blended levels without having to perform turn-based generation as in prior work. And in the following slides, I'll describe each of these two parts in a little more detail. So first we look at the sequential segment generation using our modified VAEs. So for this, we train models for each of Mario, Kid Icarus, and Mega Man, as well as on the blended Mario and Icarus domain, which is just the levels of both games taken together. Now you can find more technical details about implementation given in the paper, but just as a quick overview on VAEs, regular autoencoders are neural nets that learn lower dimensional representations of data. They consist of an encoder, which converts the data into the hidden representation known as latent space, and a decoder, which reconstructs the original data from the latent space encodings. Variational autoencoders make this latent space model a specific probability distribution, such as Gaussian, which allows learning a continuous latent space, which in turn enables generating new outputs using operations such as sampling as well as interpolation, similar to such operations using GANs. The VAE is typically trained by minimizing a loss function that consists of two terms, the reconstruction error and the KL divergence between the latent distribution and a known prior. Minimizing the reconstruction error reduces the error between input segments and the reconstructions phrased by the decoder, while minimizing the KL divergence forces the latent space to model a continuous and informative distribution. And all that we do to enable sequential generation is that we modify the computing of the reconstruction error while leaving the KL divergence as is. So typically, the reconstruction error would be computed between the segment output by the decoder and the corresponding input segment that was passed through the encoder, but instead, we compute this error between the segment output by the decoder and the segment that follows the corresponding encoded segment in the level. And so minimizing this new reconstruction error enables us to learn a sequential model of segment generation, where the encoder maps a given segment into a latent vector, but the decoder now maps that latent vector into the segment that would sequentially follow that input segment in the original level. Note that technically we're no longer auto-encoding, but the rest of the VA loss formulation is the same, and the simple modification does enable our approach. So using this new formulation, we obtain the generative algorithm shown on the slide, where we take as input a start segment and the number of segments n that we want to generate, and by following an iterative loop of encoding and decoding, where we generate a new segment, use the newly generated segment as the input for the next iteration, and continue for n segments, we can generate a sequence of segments that follows a logical gameplay progression, and hence can be combined into a full coherent level. So that was the first part of the approach, which gives us a sequential segment-based level generator, but this still only improves upon existing approaches along one direction. To generate levels that can dynamically progress along any direction, we need to determine where to place a generated segment in relation to the previous segment. So for this purpose, for each domain, we trained a random forest classifier on segments, using the direction of the next segment as the labels for the inputs. So for this, the inputs are the same segments as the inputs for the previous part, but now we also have labels where each label is the direction where the next segment appears in the original level. So given an input segment, the classifier learns to predict in which direction the level should progress after that segment. And as two examples, we have Mario on the left and Mega Man on the right. In Mario, all segments, of course, have a right direction label, but for Mega Man, this varies depending on the segment. So the segment highlighted in red would have an up label, because after that segment, the level progresses upward, but for the segments towards the beginning and end of the level, this label would be right. We trained the classifiers using a 70-30 train test split for each domain, and as shown on the slide, obtained high accuracies for each of them. But we note that we did have to perform some post-processing after prediction to deal with certain situations regarding incorrect predictions for segment placement when generating levels. I'll skip these for time, but the details are given in the paper. Overall, combining the classifier with the sequential segment generator gives us our final generative pipeline. So we get a sequence of level segments using the generate level algorithm that we discussed in the prior slide, and then using the classifier to predict labels for these segments, we get the directions in which to place these segments to be able to lay out the entire level. So, to test our approach, we used a three-part evaluation focusing on 1, the continuous nature of generated levels compared to a baseline, 2, the properties of generated blended levels, and 3, the quality of generated levels that are arbitrarily long. So first, to test if our method generates levels that have a good sense of progression, we introduced a discontinuity metric. We define this as the absolute distance between path tiles along the adjoining edge of 2 successive segments. So if 2 segments are connected horizontally, we compute the displacement between the path tiles on the column to the edge connecting the 2 segments. Similarly, for segments connected vertically, this is computed using the rows at the edge of the 2 segments. If a column or a row does not have a path tile, the metric returns 16 by default, since that's the maximum column height and row width. Overall, thus lower the value for a pair of segments, the more continuous is the path between them. And the reasoning behind this metric is that levels with better progression would likely have a more continuous path for their segments, rather than a path with a lot of displacement between where it ends for one segment and where it begins for the next. This, of course, is not some perfect or ideal measure of level progression, but it does give a sense of the nature of the path through level, and at the very least gives us something with which we can evaluate our approach. For evaluation, we computed the average per segment discontinuity for 100 generated levels each for Mario, Kid Icarus, Mega Man, and the blended Mario Icarus domain using 2 methods. 1, using our generative model, which we call sequential, and 2, by randomly sampling successive segments, which we call independent, since the segments are sampled independently of each other. The generated segments in both cases were then placed using our directional classifier. Each generated level consisted of 12 segments for Mario and Icarus and 16 for Mega Man, since those were respectively the average number of segments and levels from the original games. For the combined Mario-Icarus domain, generated levels consisted of 12 segments. And as the results in the table show, for all games, the sequential method led to significantly lower discontinuity values than the independent method, thus suggesting that levels generated using our approach have more continuous paths through their segments. Note that the differences are greater for Mega Man and the blended Mario and Icarus domain, since, as we have discussed, segments generated using the independent method for these two often leads to levels that are not traversable, because successively sampled segments may have different orientations, whereas for Mario and Icarus, because they progress in one direction, the independently generated levels are often playable, even if they're not as continuous as the sequentially generated ones. So here we have some example levels using both approaches, and there are a lot more examples given in the paper, but just based on visual inspection of some of these examples, we can see that the sequential method generates levels with a more continuous flow from segment to segment as compared to the independent method. And here we have examples of levels blending Mario and Icarus. And again, here the sequential example has more of a continuous flow to it and is mostly playable as compared to the independent example. So that brings us to part 2 of our evaluation. As mentioned before, being able to generate levels progressing in multiple directions also allows us to move beyond generating segments of blend games progressing in different directions to entire levels that do so. So to test blending, we generated blended Mario and Icarus levels of 12 segments each using the model trained on segments for both games taken together. We generated 6 sets of 100 such levels, with each set differing in the choice of the initial segment. The first set used an initial segment sample randomly from the blended latent space. The remaining 5 used initial segments obtained by interpolating between latent vectors corresponding to actual Mario and Icarus segments at intervals of 25%. So, doing this, we obtained 5 such sets, 2 beginning with the original segments, and the remaining beginning with the 3 interpolations, with the numbers indicating the distance interpolated from the Icarus segment to the Mario segment. And to evaluate, we looked at the proportion of Mario-like and Icarus-like segments that were generated for these different sets of blends. Since we know that Mario and Icarus levels progress exclusively to the right and upward respectively, we can use our directional classifier as an evaluation proxy. That is, blended segments classified to have the next segment be to the right can be deemed to be more Mario-like, while those classified to have the next segment be to the top can be deemed more Icarus-like. Results for this are shown in the table, and we see that levels generated from random latent vectors perform the most amount of blending, while those generated from interpolated vectors heavily favor the game with a higher proportion in the interpolation, mostly ignoring the actual proportion itself. So, while this approach is successful in generating blended levels, in the future, we'd like to improve it so that the nature and amount of blending is more controllable. Additionally, we compared the blended levels with the original Mario and Icarus levels using 5 tile-based metrics. And the results show that the values for blended levels fall mostly between those for the original Mario and Icarus levels, suggesting that the properties of the generated blended levels do in fact blend those of the 2 original games, especially in terms of density, path prop, and nonlinearity. Leniency and interestingness for blended levels are between those from Mario and Icarus also, but not in the expected pattern, and this speaks to the generated levels having fewer enemies, hazards, and collectibles than the original levels. For our final evaluation, we wanted to test if we could generate arbitrarily long levels without the quality or characteristics of later segments deteriorating. So we generated 100 levels of 120 segments each for Mario, Kid Icarus, and the blended Mario Icarus domain, and 100 levels of 160 segments each for Mega Man. So levels that were approximately 10 times the size of an average original level, so pretty massive compared to the original levels. And for these, we computed the per segment average discontinuity and tile-based metrics defined previously for each of the 10 subsections of these bigger levels to see if there were any changes to these values as the levels got bigger, with more and more segments being generated conditioned on the previous segment. Results for this are shown in the slide. And to better understand these charts, you can think of the x-axis as sort of the temporal progression of the level. So 1 on the x-axis corresponds to the average values computed for the first set of 12 segments, 2 on the x-axis corresponds to the average values for the second set of 12 segments, and so on. Note that ideally we'd like to see little variation in terms of metric values for all 10 sets of segments, so the straighter the trend lines, the better. And this indeed bears out in the results for all metrics and games. The exception is discontinuity for Mega Man, shown using the gray line in the lower right chart, which actually seems to get lower as more segments are generated. A possibility for this is that the Mega Man model might be falling into a pattern of generating similar segments over and over again, causing little variation in path and hence low discontinuity. This ties into the broader problem of latent models suffering from posterior collapse or mode collapse, where the decoder sometimes ignores a subset or, in the worst case, all of the latent space. More details of this are given in the paper, but we note that we only encountered this when trying to generate these massive levels, and also only for Mega Man, so it isn't really an issue in general when generating more regular size levels, but is nevertheless something to consider in the future. So, in conclusion, we presented a new PCGML approach that combines the use of a modified VAE and a random forest classifier to produce a model for sequential platformer level generation and blending. Our results show that this enables generation of more coherent platformer levels than past approaches, generation of platformer levels that progress in multiple directions, blending of levels from games that progress differently, and generation of levels that are arbitrarily long without suffering from a loss in quality. There are, of course, several considerations for future work. We could compare classifier-based segment placement with other placement strategies, such as using heuristic methods or optimizing for specific metrics. Additionally, while our approach can generate levels for multi-directional platformers such as Mega Man, there is great room for improvement in terms of quality of models and generated levels, and reliability of generation and controllability, all of which should be investigated in future work. Moreover, none of the games we used had levels progressing from right to left, such as levels in Ninja Gaiden, for example. While our classifier was trained to work with all 4 directions in mind and should work as is for right to left progression, this needs to be empirically validated in the future. Finally, while our method allows for generation of traversable blended levels, the current approach does not have any direct means of controlling the blend proportions or any other aspect of the blended content. So adding more controllability to blending is something we'd like to do moving forward. And that brings me to the end of the presentation. Thank you for your attention.
Okay, we have time for questions. And once again, go ahead and raise your hand or type in chat. Phil, you can go first.
Hi, thanks for that. Interesting presentation. One question that kept popping into my head was the fact that you're essentially applying a sequential model for a level that, for my mind, sort of has structure at different scales. So I guess the question is, have you thought about how you look at the different scales of the content in terms of not just individual segments, but also the overall layout of segments? And that is maybe part of the problem is the fact that you're treating it as a sequential model when it's actually kind of a more structural thing, but the structure is at different sort of scales. Typical sort of CNN kind of problem, right? Where you've got small scale things and large scale things, and they both contribute.
Yeah, so yeah, in this work, we sort of did look at it as a sequential problem because there has been prior work in generating levels sequentially, but not at the segment level. There is work out there that looks at it as a global problem. Like one of the works that I referenced was the dungeon generation problem, where they generate a graph of an entire dungeon and then generate the rooms separately. That is something we want to look at in the future, but yeah, for this work, we didn't do that.
Okay, I believe, let's see, my co-host had a question.
Yes, I was interested by the long level generation you mentioned and the sort of potential of mode collapse. And I was wondering, is that a result of sort of feeding the generated sequences over and over again into this model? Like, is it sort of drifting then, or like could this happen at any phase of the sequence generation?
Yeah, I think it is a case of drifting. I think what's happening is there are like regions of the latent space that basically the generator gets trapped in, right? So, and this only happened in Mega Man, and like I said, only for like large levels. So I guess the challenge is to avoid learning those regions of latent space. But yeah, like what you said is correct. It's basically because it's like an iterative loop of encoding and decoding. It's sort of guiding, in certain cases, it's guiding the generator towards these regions of the latent space that's basically like just the same segment over and over again, and that's what's happening.
I've actually got a follow-up question to that, which is, do you think more training data would have helped there?
Yes. In general, for more training data would help. I think arguably like the biggest challenge of a lot of our methods is there's not a lot of training data. But yeah, finding like some sort of a balance between training data and how strong or weak our architectures are, that's sort of one of the biggest problems of PCGML.
Do I just ask a question or do I wait to be called on?
Well, I will call on you now.
Thank you. I appreciate being called on. Great presentation, Anurag. So I had a question about sort of where you go from here. Because what this workshop, this paper lets you do is sort of automatically determine the relative position of level segments. So my question is, how do you imagine this being used by either a person or a further system? Is the idea that you're generating level segments and then just placing them using this random forest classifier? Is a person deciding what kind of segment to make, and then the random forest classifier is saying where to put it, et cetera, something completely different?
Yeah, that's a good question. Kind of some version of everything you just said. Putting a human in the loop, deciding on what the content of an individual segment is, where to place it. You could think of really as many uses of this type of system as your imagination can let you. The goal is to make some sort of a co-creative system where, in one iteration of the process, the designer in the loop can decide what to put in the content, and the next iteration where to put a generated content. But yeah, there's like a lot of ways in which we could take this work in the future.
Technically, we are running ahead of time, so I don't know if we want to try and bring the schedule more in line with the advertised schedule or not, though I think all our remaining speakers are here already. Okay, I have one speaker voting to go earlier, but I will say I am going to suggest we still take our break, because if nothing else, I have been up since 4 something this morning, and I could probably use some more caffeine. So with that in mind, shall we reconvene at 5 after the hour? Join us then for more PCG workshop excitement. Okay. It is 5 after the hour by my clock. And Jim looks like he's ready. So let me paste the, well, I guess Jim already put a link to slides in the chat, but I will include that. So we have our next paper is Spatial Layout of Procedural Dungeons Using Linear Constraints and SMT Solvers by Jim Whitehead, presented by Jim Whitehead, who appears to be at his office in UCSC, which is these days a very special occasion.
Right. Thank you, Isaac. Whoops. Let me go ahead and start sharing. I guess maybe first of all, before I start, let me just give kudos to Ann Sullivan for this beautiful Nyan Cat quilt that you'll see in the background here. Okay, let me go ahead and share screen.
Yeah, let me know if we, okay, good, it's working.
All right, look good? Okay, great. So in this talk, I'm going to be giving a presentation about how to do dungeon layout using SMT solvers, which is a new kind of constraint solving technology that so far in the PCG community, we haven't explored that much. So as many of you are aware, dungeons are super common in fantasy games. Dungeons in the PCG community go back a long way to the game Rogue, developed by, yay, UCSC students, Toy and Wickman back in the early 1980s. As an aside, Toy spent too much time doing Rogue and did eventually actually fail out of UCSC, but he's been relatively successful ever since. Okay, when you do dungeon generation, there are generally, as a generalization, 3 different phases. The first phase, which is often omitted, is the mission phase. And so that's when you determine the overall goals, the puzzles, especially lock and key puzzles, and the various orderings of those goals and puzzles. But again, this is often very complex, and sometimes generators don't do that. Once you have the missions, or if you don't have the missions, you then proceed to the room layout phase. This is where you generate a series of rooms, or you select those rooms from some library of rooms, and then you place them in space consistent with the set of constraints of various kinds. Finally, once you have all those rooms, you then go ahead and connect them. The final phase of interior decoration, you end up placing monsters and treasures inside those rooms, and then you're able to present those rooms to the player. Okay, so focusing just on that room layout phase, we then go into diving in there. There's 3 steps within that room layout phase. So the first one is you end up having to select your rooms from some existing library, or you randomly generate rooms of various sizes. Once you have that set of rooms, you then have to place them. Usually there's some kind of a fixed play field. Most typically you don't have an infinite play field. It does have a fixed size. And you have to place them, and you have to place them such that there aren't overlaps. This layout phase is the focus of the current paper, though the generator that I've created and does actually do all of these phases, but really the kind of research that's taking place is in this layout phase. Finally, once you have the layout phase done, you can go to the connection phase where you connect all those rooms together with passageways and doors, sometimes secret doors. Okay. When you're doing dungeon layout, the key challenge is placing rooms in the playfield while avoiding overlaps. So this lack of collisions, this is the key problem that almost every dungeon layout solver is trying to solve. There have been a lot of different approaches in the literature for how to do this. I guess one that inspired me to some degree was the one that you have the animated GIF on here. This showed up in a Gamma Sutra article many years ago. And the idea here is it generates a whole bunch of rooms, then does this force-directed layout, selects some number of those rooms, then ends up computing a minimum spanning tree, and then kind of takes just some of the nodes off of that minimum spanning tree and uses that to make the connections. And so in fact, in my dungeon generator, I use that same approach of a minimum spanning tree and then using that to create connections. Existing approaches have a number of problems though. First of all, like in that force-directed layout approach, there ends up being uneven distribution of rooms. If all of your rooms begin at the center and then they're kind of forced out, you're going to end up with dungeons that typically don't end up having rooms in the various corners. They're going to be sort of circular in nature. So there are some approaches where you end up partitioning the space. You essentially make a kind of quad tree over your play field and then place rooms inside that quad tree. But this makes it that some room locations are just inaccessible because the quad tree is not able to accommodate subdividing the space in every possible way. Sometimes there are different approaches where you just end up having the potential for no solutions. So there's some approaches where you essentially just keep placing rooms, and if you end up with a collision, you sort of backtrack and then try placing randomly in another spot and another spot. But you can end up in situations where there just isn't any solution and then you just end up having to backtrack. And so either these approaches don't have backtracking and then they can end up with no solutions, or they do backtracking and then that can get exponentially slow. Other approaches sometimes have difficulty in handling multiple large rooms. These are those space partitioning approaches. All of the approaches do have this challenge though, that they can't handle multiple simultaneous constraints. So you can sort of think of a lot of the existing approaches for dungeon layout as being, I would say, kind of like community developed constraint managers that only handled the one single constraint of avoiding overlaps. But if you want to add additional constraints in there, well, then that ends up being a problem because they really are only designed to handle collision avoidance. but you might very well want to have other kinds of constraints. So the first two constraints listed here are the ones that most dungeon generators, dungeon layout generators handle. So within a playfield, all the rooms have to be inside the playfield. That's sort of a basic one. And then no overlaps, which we've been talking about. You then might want to ensure that your rooms have to be a certain distance apart, so that they are kind of seem nicely spaced and they have rooms for those corridors. You then could imagine having some designer constraints on top of that to give the designer greater control over the kinds of dungeons that you'll be creating. So one is to place rooms along a particular control line, and then they have to be a specific distance within the control line. So as you can see in that C-shaped dungeon on this page, the red lines there are the control lines, and the dungeon generator was able to place rooms in proximity to those red control lines, and you then end up with this, C-shaped dungeon. Okay, now in a given game, maybe you don't want, particularly a C-shaped dungeon, but you might have other specific design constraints that would lead you to create a line that would be, suitable for the particular game that you're developing. Another kind of constraint might be that you want to have certain rooms be in close proximity to each other. So for example, in the example here, there's a very large room, which I'm declaring to be the throne room. Got to use your imagination there. And then sort of on the bottom of that is kind of a waiting room. That's maybe where the nobles wait before they're called in to see the king. And then there's a little tiny room next to that throne room, and that's I'm calling the escape room. So if some huge battle breaks out in the throne room, the king can or queen can easily escape to the escape room and then get away quite easily. So you have constraints where the antechamber needs to be exactly underneath the throne room, and then that escape room needs to just be kind of towards the upper top, and they have to be physically connected to the throne room. So those are examples of these like room proximity where certain rooms have to be exactly next to each other. The control line and the room proximity are the only designer constraints I explored in this paper, but you can certainly imagine that there could be lots of other kinds of designer constraints that you might want to have. Okay, so you have all these constraints. How do you go about finding dungeon layouts that satisfy them? This was a journey that I ended up taking throughout the past year. I started looking into geometric constraint solvers, the kind of constraint solvers you might find in CAD tools. And while they certainly have the ability to find solutions of this kind, I think, they tend to be oriented towards finding just a single solution. And I think they also tend to have a hard time when you have like multiple different options, where like rooms could be sort of oriented this way or above each other and so on. And then also the big killer was there just aren't really readily available solvers in open source form that you can play with. I spent a long time hunting for good open source geometric constraint solvers to play with, and did not end up finding any that seemed easy to use, had good documentation, code was freely available, and so on. Okay, what about answer set programming? Well, when I started, my going in assumption was it appears to really only work in grid worlds. And while you could sort of think a large playfield as a kind of grid world, it seemed to me that that was maybe not quite the right approach. But I'll have more on ASP later. I then started looking at UI constraint managers, and in particular looked at one called Cassowary, which was developed for handling constraints between widgets and a user interface. Cassowary is still widely used today, and in fact, as I understand, both on Android and on iOS, the user interface constraint manager is using Cassowary underneath the hood. But the problem with Cassowary, when I looked into it, is that it just, it had this assumption that all of your constraints were ANDed together. And I wanted to be able to say that, say two different rooms could either be like above each other or below, or to the left or to the right. And so that ended up being a challenge there. Okay, Isaac's giving me a time. I think I'm probably going to be the one that blows the timing on this whole workshop by going over. So I'll go over a little bit, but I do have a timer going to. Okay, so this led me to Z3, which was an SMT solver. Now, SMT is like a super unfortunate name. You can think of SMT as just like a constraint solver that can handle a very wide range of constraint types, including among them linear constraints. The name like is just like super geeky into the verification community. You can sort of think of it as being like satisfiability, which is Boolean sat solving, modulo, which I think very roughly in this sense means making use of, and then theories, which are just a bunch of additional ways of dealing with different kinds of constraints. I'm going to be focusing on linear integer constraints here, but SMT solvers can handle a very broad range of different kinds of constraints. Okay, what do I mean by linear inequalities? So these are equations that kind of take the form of, equations that have like a less than or equal to, an equal to, or a greater than or equal to, where all the variables are integers and all of the constants are integers as well. And so when they're in that case, they're all linear integer constraints. Each of the equality or inequality expressions, we call that a clause. And then in SMT, all the clauses can either be anded or ored together. The nice thing about integer constraint solving is that generally tends to be pretty efficient. For those of you who know what simplex is, it's basically an advanced form of simplex solving underneath the hood. Same thing for cassowary. I think what SMT brings to the table is it brings search on top of the simplex. Okay, so two example kind of constraints. So this within playfield constraint. So you have a room there, it has a width, it has a height, and then you have a playfield, which has a width and a height. And the constraint is that, well, the upper left x has to be greater than 0, the upper left y has to be greater than or equal to 0, and sort of the x plus width has to be less than the playfield width, the y plus height has to be less than the playfield height. When that kind of gets expressed in Z3, which has a Python binding, what you see below, you have a solver object, and then you call the add method on that solver object, and then within the parentheses, that's then the particular linear expression that you're then passing along to the solver. Okay, there's then the no overlap constraint. So you have two situations where two different rooms, which we'll label I and J, so you could either have J above I, or I could be above J with a kind of separation between them. Or it could be to the left, J could be to the left of I, or J could be to the right of I. And these all end up being expressed using the equations that you see over there. And you all just end up, oring these all together. So it's, above or below or left or right. And this ends up handling that situation where, the things can be in different orientations with respect to each other. So this use of ORs is what really separates kind of SMT's power versus cassowary. And the reason is that these ORed constraints create a generative space. So each time you have things ORed together, it creates this possibility that it could be, one or the other, one or the other. And in this case, each of the overlap, all of these overlap constraints together create 8 possible relative positions. These are kind of different possible worlds, depending on the orientations of the two rooms. And so one of the implications here is that the SMT solver has to end up like searching through all of these different possible worlds to end up finding ones that are consistent with all the potential constraints that have been assigned. Okay, so there's 2 questions that we're interested in. How much time does it take for SMT to do these dungeon layouts, and how uniformly are rooms placed within them? If it takes too long to generate a dungeon, well, it's not useful. And also if the SMT solver returns the same solution all the time, then that's not going to be very useful for generation either. Okay, so we had this experimental setup where we have like a standard situation, no constraints except for the basic within, playfield and no overlaps. And then we had a 5-line where you had these 5 different control lines and you had to generate along the control lines. For each situation, we generated 10, 20, or 30 room dungeons. We did this 100 times. We did 50 runs of those 100 generations, generated 5,000 total generations. All right, what does that look like? So the layout times, we have the layout times are on the x-axis, the number of instances are on the y-axis. And you can see that, as you get more rooms, the time increases. The ticks along the bottom are outliers, and so you can see that there are some outliers. Generally, they're between 2 to 7 times the kind of more median here. I think the other thing I would observe is that these are generally not normal distributions. They're more of what I would call a Weibull distribution, although I should be clear, I didn't do like a check on what kind of distribution or a distribution check. And then this is sort of some more detail on the particular layout times. I guess since I'm running over, I will sort of not go into this in too much detail, except to maybe say that as the total number of clauses goes up, the total solving time goes up as well, and it seems to be lightly exponential in terms of time. Okay, let's see. So I think I've gone through that. I guess maybe the high level here on layout time observations is SMT solvers are fast enough for use in games. So then spatial uniformity, we did more or less a similar situation, standard and 5-line, slightly different numbers of units for the room sizes for the 5-line, and then slightly fewer runs because some of the runs were taking longer. To create the heat map, we took our playfield and turned it into 5-unit bins. And then if a room overlapped a single bin, then we would sort of increase the count for that bin. And so as the number of counts increase, the heat value increases. And so the idea is that this heat map can give you a kind of sense of, just how often was a dungeon in that particular location. Okay, so a couple observations here. One, in the 10-room setup, especially for the standard, you can see that things are kind of clustered in that upper left-hand corner. And so that is showing that there is some bias in solutions, at least for 10 rooms, towards those upper left solutions. But as you get to 20 and 30 rooms, that bias tends to go away. Although especially visible in the 30 room, we do get this interesting artifact where these are these kind of dark lines that are appearing, and there's also some kind of line effect sort of in the middle there as well. We also, in the control line case, we're seeing how there is some clustering along the edges of the control line, and you can see some definite square-like artifacts there as well. Okay, so some observations here. There definitely are some hotspots in that 10-room layout. The control line solutions definitely seem to cluster around the boundary edges. And there are these artifacts of the darker lines and squarish hotspots. I'm thinking this might be something to do with the room sizes, but it might also be telling us something about how the SMT solvers go about solving things too. I think this means SMT solvers are relatively good at sampling the solution space, but there are some artifacts. Okay, related work. So for me, one of the interesting things about the related work here is once you started looking at this problem from the perspective of constraint solving, it started making some connections to other different kinds of related problems much more visible and obvious. So one, there is this well-known problem, the interior layout problem. And if you view that as a constraint solving problem, it's placing furniture within a room subject to constraints. And so this is similar to dungeon room layout because the furniture shapes can be similar to dungeon rooms. They're inside the walls of a room, which is like inside the walls of a playfield, no overlaps, and there are separation, adjacency, and control line constraints as well. Well, there's this old paper from 1975, showed up in CACM by this fellow Pfefferkorn, and he clearly, describes a constraint-based approach for doing interior layout. At that time, people were writing their own custom constraint solvers. They didn't have something as sophisticated as SMT, but you can clearly see them viewing this kind of problem as a constraint problem. In a similar way, there's another problem called the architectural room layout problem. So if you're placing rooms within the walls of a building envelope subject to constraints, there's, it's either room layout, building layout, space layout planning, spatial layout, a bunch of different names that this goes by. And again, very similar to dungeon room layout is placement of room shapes inside the walls of a building without overlaps. You don't generally want a separation. You, in this case, want things to be immediately adjacent. And there's this constraint that you want to fill the building envelope. But again, very, very similar problem. And the survey by Humayuni in 2006, trace this work back to 1965, and there's others who found precursors even into the 1950s for this literature. There's another really well-known problem called the bin packing problem. And in the bin packing problem, you're placing a series of rectangular shapes onto a larger surface, subject to constraints. Again, really similar to dungeon room layout. The big difference here is that in bin packing, you want to do optimal placement. And the idea is that you're trying to minimize the amount of space used by all these bins. And there was this nice master's thesis where they actually took a look at the use of SMT for bin packing and ended up with a number of linear constraints that look remarkably similar to the ones in my paper as well. So again, if you look at dungeon room layout as a constraint solving problem, all of a sudden you start making all these connections to several classic layout problems, and the literature and the prehistory in this area goes way back. Okay, what about ASP? So ASP can also generate content using constraint solving. How does it compare? I think this is a really, really deep question, and in some respects, the answer is more research necessary. I wasn't aware of ClinCon, although Adam Smith is probably like right now gritting his teeth and saying, "Jim, I told you about this years ago." Anyway, whatever, it came in, it didn't stick. I didn't think about it. But ClinCon does have this ability to do linear constraints along with ASP. So it seems to have similar expressive power as Z3 for linear integer constraints. It seems to come from, Z3 seems a little easier to use from higher level languages, but ASP is its own programming language. SMT does have its own language, but it's more around interop. Really unclear performance differences. So how can we compare these different solvers? I don't know. I think this is an open research question. I'd love to see some more research on this. Okay, so in summary, I've presented an approach for dungeon layout using linear constraints. SMT solvers appear to be sufficiently fast for use in game projects. Solution space sampling is good, but with some hotspots. And the history of constraint-based layout is really long, going back to the 60s, 70s, and even 50s at times. All right, thank you. I'm done, open for questions.
We don't have a lot of time for questions. Though if people do have questions, you can post them in the chat or on Discord.
Right. I'd be happy to look there as well.
Yes. I have some questions for you, Jim, but later.
Okay. I look forward.
Yes, I know where to find you, so I'll let everybody else ask the questions. Matthew, are you ready?
Yep. You should have my pre-recorded presentation, I think.
Yes, we do have that.
Good.
I got it.
Thank you.
Yes. I do want to thank, since we've got a sec here, I want to thank Lisa for all her work on the recordings. And yes, I will reshare the Discord link just a sec, unless somebody else beats me to it.
All right, so looks like the Discord link got posted. Isaac, you want to announce the paper?
Yes. Up next, we have tabletop role-playing games as procedural content generators by Matthew Guzdial and company. Because this is a quite impressive list of people.
Okay. Hi, my name is Matthew Guzdial, and I'm here to present the work of a lot of people, including myself, entitled Tabletop Role-Playing Games as Procedural Content Generation. This is work from myself, Debbie, Max, Mike, Miriam, Antonios, and Anne. That's right, we've got 4 M's, 2 A's, and a D. Pretty darn good, I think. Now, what the heck is this about? Well, we're going to be talking about tabletop role-playing games. If you're not at all familiar, if I'm saying these words and that means nothing to you, high level, you've got a group of people. They're going to be working together to tell a story in which they are role-playing as characters, distinct from themselves. Basic idea. The tabletop bit means that you're generally playing on a tabletop, either a physical one or, especially these days, a virtual one. Now, if I say tabletop role-playing games, that may sound unfamiliar, but a thing you've almost definitely heard about is Dungeons & Dragons. Dungeons & Dragons is an example of a tabletop role-playing game, but despite what you might have heard, it is not the only example of a tabletop role-playing game. For example, you have things like Honey Heist, which is a game in which you play as a group of bear criminals on a heist for some honey at a honey convention. Or games like Mutants in the Night, worked by Orion Black, who is inspired by X-Men. Should note, Honey Heist was written by Grant Howitt. So, huge variance. And tabletop role-playing games are gaining increasing attention in terms of things like graphic novels, such as The Adventure Zone, animated series, such as Harmon Quest, and, of course, fast food advertising deals, as with Critical Role playing a Wendy's tabletop role-playing game. And you also have merchandise, like pins, puzzles, and of course shirts. I should note, I'm wearing a Friends at the Table actual play, which is a tabletop group that does a podcast. I'm wearing one of their shirts right now, so I'm very clearly biased. I very clearly think that this is an interesting area to be working on. But you may not be, and you might be asking yourself, well, why should me, a PCG researcher, care about this thing? Well, here's our thesis. Tabletop role-playing games can be understood as an example of PCG. And they are an underexplored application domain for PCG. So, quick introduction to tabletop role-playing games, because you're going to need a little bit of a better idea of what these things are before we can move forward. So, in the moment-to-moment, a tabletop role-playing game tends to look like conversations between people or narration by a specific person. Now, often you're going to have some kind of thing on your tabletop, for example, a like battle map or game map, which has different icons indicating different characters, different items, and a whole background for the space that you're in. Now, these things together can go on for quite some time, where you're just having a conversation, just talking, just narrating events, until you hit a conflict point, or a point where you need some resolution. At that point, you tend to rely on dice, though not always. So sometimes there's conflict resolution mechanics that use playing cards, or that ask you to have even more interesting ways of resolving conflict. Look outside at the moon, things like that. Now, this random noise, this whatever it is going to be interpreted by the game's mechanics. So by rolling a certain number of die, I could, for example, figure out, according to the game's mechanic, whether or not I hit a goblin. And then that is translated into more dialogue, more narration, etc. That's what the moment-to-moment is like. Now, over a session, there's going to occur, which is sort of a longer period, like a few hours where you're playing a tabletop role-playing game. This is going to repeat many, many, many times. Often is going to be guided by one player in particular, who often has a role called Game Master or Dungeon Master. This role is sort of like a director for the story, but you're not the sole sort of owner of the story being produced or the experience being produced. Instead, you could actually have a GM-less game, or you can have a game which is being run on a module, which is sort of this pre-authored thing that says, hey, here's the kinds of challenges you're going to face, sort of giving you prompts to keep going forward from there. Okay, so let's jump back to this thesis. And I'm going to focus on this first part especially. Tabletop RPGs can be understood as an example of PCG. So let's think about this for a second. Let's imagine tabletop role-playing games under a PCG lens. What does that mean? Well, I've already introduced this sort of like pipeline, or this process of random noise translated by mechanics and then translated by people into events. But this is broader, right? So we can think about a particular group playing, for example, D&D, or a particular game. Sorry. We can think about a particular group playing a game, so mechanics and some random noise, and producing a narrative, right? Over a period of time, these sort of events are going to string together and form a narrative. But this is not just one kind of narrative that can be produced. So while you might think about tabletop role-playing games and immediately say, okay, well, you're going to be playing Dungeons & Dragons, and you're going to make a story like The Lord of the Rings. A lot of the time, if you talk to somebody who's played Dungeons & Dragons, you're going to find that actually the output stories are something more like Shrek. Or, as is often the case, you'll end up with a group that takes Dungeons & Dragons and decides to play a game in a completely different setting, like Firefly, for example. An old TV show, which is sort of a combination of like Old West and space sort of settings. Now, at this point, you might suggest, okay, you should be playing a different game, and there's lots of different games, and they produce different things, and they can even go beyond narrative. So, for example, The Quiet Year by Avery Adler produces both a map of the town, the village you create while playing the game, like an actual map you can look at, plus the story of that village, is sort of looking over time in a final year until it is attacked by some outside force. Highly recommended. Instead, you don't actually need to produce a story at all. So in Oh No, Bro, You Thought Too Hard About the Bangers, Bro, he specifically warned you not to do that, and now you fell into the banger singularity, bro. Almost said that completely right without messing it up. We have from Taylor LaBreche, I should note, this game just sees you role-playing to produce a playlist, a music playlist, a playlist of songs, with no notion of creating a narrative. In fact, Taylor specifically rejects this notion of you have to produce a narrative from your games. Now, there's this other interesting thing you can do here, because it's not just this one process, but you can hook these processes into other things. So, for example, we could take our map and our story that we got from Quiet Year and plug that into the experience of playing a different game to produce another story. And this is exactly what the Actual Play podcast, Friends at the Table, did with their Marielda season, in which they used The Quiet Year to create a town named Marielda, and then they played John Harper's Blades in the Dark in that town. And this reminded us of PCG pipelines, the idea of putting together different generators, in this case, some of them games, some of them random number generators, and some of them people, in order to produce a final output. Now, this is a paper, in this case, a figure that I took from a recent Rosine Tadelia's paper. Now, in terms of that second bit, the underexplored application domain for PCG, this one is a little self-evident. Now, there is some work, for example, Horswell et al. On generating play sets for the game Fiasco, or some recent work from Ferreira et al. On computer-generated music for tabletop role-playing games. There's really not a lot there. But that's okay. But that's okay, because we think that you and the rest of us can fill in that gap, and that relative unexploredness is really exciting. So for the rest of this this presentation, whatever I can fit in, I want to go over just a couple examples of cases that are particularly interesting about the intersection of PCG and tabletop role-playing games. So for example, possibility space is known to PCG people. It's the idea of the output, the entirety of the output of the generator, right? And controllability, similarly, is about how can we control that output. The safety tools probably isn't a term you've heard of before. So as an example of this, we have things like the X card from John Stavropoulos. And the idea here is that with the X card, you're sitting around at a table playing a game, and you can put down the X card and say, no, that didn't happen. Whatever just happened, it didn't. And this is a way of avoiding things at the table like trauma or just tropes that are just overused. But what it really accomplishes is a way of shaping the output of the generator as it's going. How often in PCG, a grammar-based generator, do we say, oh, that last step of the grammar, don't do that, go back and do another one? Relatively infrequently, I think. But I think there's a lot of possibility there. Similarly, there's a notion of lines and veals from Ron Edwards. The idea of a line is it's a line that you're not going to cross. It's sort of like a way of adding like a constraint in like a constraint-based generator of saying, if we have this in the game, it would be invalid output of our game. A veal then is a way of saying, sort of like a soft constraint. It's saying, okay, this can be in the game, but if it's in the game, we're sort of going to fade to black. So for example, you might say, we're going to have a veal on sexual content. I'm totally fine with it happening, but it's going to be off screen. You're sort of going to have the camera pan away during a romantic evening or something like that. And this is an interesting notion because, again, it's like a soft constraint. It's an idea of we're going to shape the output of our generator by saying this is going to exist, but it's not actually going to be part of the output we're all looking at. It's just going to be understood, which is not a thing that we're familiar with, at least in classic PCG or in the field of PCG broadly. Now we have a term here called the fruitful void, which might be a little bit novel to a number of people listening. This actually comes from the tabletop role-playing game designer D. Vincent Baker. And the idea is that when you're designing a tabletop role-playing game, you want to have all of your mechanics, everything that's systematized, be sort of rotating around or centered around a primary theme that isn't systematized. That's the fruitful void. So for example, in My Life with Master, which is a game by Paul Shegg, and the idea is that you are playing as like the hench person of an evil master or mistress. Now in this game, the idea of defiance, of defying your master or mistress, is not systematized. There are no mechanics around when you defy your master or your mistress. But instead, you have things like fear and hopelessness, which are meant to push you towards defiance, but allow you to discover it on your own. This is similar to the notion of Kate Compton's imagination playgrounds of sort of fruitful voids that we leave in generators to let people fill them in. And in her case, she was mentioning for Twitter bots. But we think that this is broadly something of interest. And when you're making a PC generator, right, how do you enforce that you don't want to output certain things to leave it up to the player? Or how, when you're designing your PCG generator, do you just avoid even systematizing certain things because you don't want to tell the player it, you want to leave it up to them to figure it out. Okay, so that's about all that I had time. Okay, so that's about all that I have time for, unfortunately. There's so much good stuff in this paper. I really recommend checking it out if I've at all interest you. And if I have interest you, hopefully at this point you're asking, okay, well, what do I do next? You've sold me. Tabletop role-playing games are great, right? Well, there's a few obvious areas of future work that we think are interesting. So, for example, things like getting transcripts of people playing these games, something that we could parse and then do more things with, machine learning, data science, etc. Tabletop role-playing game player modeling, right? What if we could model the players of the game as we're going and adapt to their needs? Things like, well, most games use what we'd think of as like a stochastic or probabilistic grammar, right? If this die number is above this, then this happens. But what if instead you used another very common form of PCG, a GA, a genetic algorithm, or evolutionary search as the primary mechanic of your tabletop role-playing game? We think that could be quite interesting. And then, of course, there's tons of places you could put an AI in terms of the PCG pipeline, right? AI for generating events or characters, or even an AI player. Lots of cool stuff you could do there. Finally, 3 big last takeaways. Tabletop role-playing design is PCG design. That means that we can study it as an example of PCG design. Tabletop role-playing games are a great venue for PCG work, and please read the paper. And so finally, thank you so much. From all of us to you, thank you.
And thank you. We do have time for questions. Though apparently in Discord, the question is, when are we playing Dungeons in Dragons, as Antonius points out. Oh, you had something?
No. I was just going to read out this question that Tristan asked.
Go for it.
Sure. So Tristan asks, does this have to be just tabletop role-playing games? Seems like there are several non-RPG board games that could also produce usable artifacts, e.g. Call to Adventure, Hero Characters, Villages of Valeria, Charterstone, Villages Settlements. Thanks for the question, Tristan. I would highly recommend checking out the panel, Games as Story Generators, that should be showing up later in FDG. But to answer briefly, we do think that this is probably broadly true of at least a whole class of games, that you can do this kind of reframing of them as generative systems. But we wanted to focus specifically on tabletop role-playing games because there's such a strong link between most tabletop role-playing games and generating stories. I'll be. Oh, sorry, go ahead.
Yeah, thank you very much about this talk and also a great paper. I was actually kicking around some similar ideas a while back, and I was wondering about something very specifically. So one of the things with tabletop role-playing is I also find that there's a lot of like error fixing happening with players. So I was wanted your take on it. So I imagine, sometimes PCG doesn't really work, but if you do that in a computer game, it can like break the game and do all kinds of horrible things. But if something doesn't work, like imagine, you want to output Dungeons and Dragons, but it says, well, you're now playing Dungeons in Dragons, and players go like, oh, well, I guess we are. And then you just, kind of fix it from there. So do you have like a view on how that could be leveraged?
So is the question sort of how do you leverage mistakes or surprising things in the improvisational storytelling process?
Yeah, or how do you kind of, could you, like, for example, use different kinds of PCG knowing that you are working in a more forgiving domain?
Sure. Yeah, for sure. So I think that there's some pretty clear like parallels you can draw here to various experimental games like Bad News, for example, right? So one of the reasons that Bad News worked so wonderfully is because you had the incredibly talented Ben Samuel there who could translate the output of a giant town generator into something that was narratively meaningful. So I think that being able to hook up even somewhat noisy PCG systems to allow for human interpretation can allow for very powerful things. Phil has a question in the chat. Can you see PCG algorithms assisting dungeon masters in keeping track of the virtual world in some way? Similarly, like in open world or West Marches style campaigns. I can see something like a system that can constantly evolve the fantasy world and offer new challenges to players dynamically. I think that that's a great place to look at doing PCG research, and it's one of the things we recommend in the paper. I do think that any kind of research that you do in this field should definitely come from a place of talking to dungeon masters or game masters, because it's very easy to assume, oh, everybody plays games like X, but you'd find if you actually talk to these people, people play games in vastly different ways. So if you want your tool to be useful, I'd highly recommend actually reaching out and doing a broad survey of folks. All right. I actually have to run, unfortunately. I was hoping we'd end a little bit earlier than this, but I'm going to just call out Antonios, who's just sitting here muted, and it now has to look up and make a face at me, which is very good. To answer any remaining questions, I'll also be hanging out in the Discord and can answer questions there. Thank you all so much.
Thanks, Matthew. I'm sorry I was subtweeting as well during your talk.
You're a little quiet there, but actually, let me check the schedule. That was our last paper. So go ahead and queue up any remaining questions you have for the authors, because I believe we have a number of the other authors in addition to Antonios and Matthew here. But meanwhile, I'd like to take a moment here at the end to thank all the authors. I'd also like to thank our program committee who did a great job on the reviews. I especially want to thank our audience who this is roughly double the number of people that we usually have at the PCG workshop. So I'm really happy that we were able to expand it to a wider audience, and hope that it leads more people to consider the work being done here and maybe contribute themselves. And finally, I'd like to thank my co-organizers. If you could both, well, I won't ask you to stand up and take a bow, but at least like mute yourselves and say hi. You've done a lot of work here. And lastly, I want to thank FDG and the conference organizers, because this has been a great experience running a virtual workshop. And I think they've done a lot of work already to make this year work despite everything.
Thanks, Isaac. Thank you very much for the saying goodbye to everybody. Thanks to everybody for being here, and thanks to the main organizers. So it has been a very smooth organization.
Mm-hmm. I do want to remind everybody that this is not the end of the procedural content generation content of FDG. There's a number of other ProcGen papers within the main conference. And since you already have registration for the conference, I would really suggest you look those up on the schedule and check them out if you're interested. Lisa, do you have anything you want to wrap up with?
Not really, but I'm looking forward to the rest of the week. So I'll hope to talk to you all more then.
Yes. I want another one last round of applause for my co-organizers, some of whom had to get up very early and some of whom are having a pleasant afternoon in Malta right now, I believe. And I believe we need to stop the recording.
I suppose that's it. Yep.
Yep. So CLU and the rest of FDG.